Hello and welcome to this video series on quantum mechanics. So I hope I can help you guys understand a little bit more about quantum mechanics. So please follow this video series, and if you have any questions, leave it in the comment section and I'll try to answer them. So what we're going to be doing is we're going to start off with a general introduction to the subject of quantum mechanics, and we'll be looking at specific applications to chemistry. So I'll warn you that quantum mechanics does require a fair bit of math. You should have some sort of understanding on differential equations, linear algebra, and perhaps even a little bit extra math would help too if you've done something in multivariable calculus. But don't worry, if there is any math that will come about that is hard, that is, that's not basic math, I will go over it and I'll try to make things clear. So hopefully the math won't be the issue here. The issue will be trying to understand the concepts of quantum mechanics. I think that's a little bit harder than the math that's involved. So without any further ado, let's start the topic. So the first thing that comes to your mind is, why do we need quantum mechanics? So what was wrong with whatever system we had before quantum mechanics? So it turns out that before quantum mechanics, we had something called classical mechanics, and we still have it right now. It turns out that classical mechanics is very good at describing things that are on our scale of things. So you throw a ball, okay? So let's say you're standing at some height h, and you're standing on a hill, or sorry, let's say you're standing on a building, and let's say you throw a ball from this building. You throw a ball from this building, and intuitively, you know that it's going to land somewhere over here on the ground. So this is the ground, and you know it will land here, and you can predict exactly where it will land based on some initial conditions. So those initial conditions might be, the velocity that you throw it at, or the angle you throw it at, this angle over here, theta. So if we know these initial conditions, then basically we can find out everything about the system, everything we need to know about the system with about 100% certainty. Okay? I mean, if you have a friend and you are playing catch with a ball, you throw the ball to your friend, and if your friend catches it, you know that it's going to be in their hand, right? You're 100% certain of that. So classical mechanics is very, very concerned about particles and waves, and classical mechanics does a pretty good job at describing the behavior of particles at a larger scale. The example I gave with your friend, and the throwing ball example, and I said that it would land in your friend's hand, and that there's 100% certainty that if it does land in its hand, you will find it in the hand. It might seem trivial. You might think that, well, that's pretty obvious. Why is this guy mentioning this? And it'll hopefully fit into my discussion when we start talking about electrons and subatomic particles. Then you'll understand why I gave this specific example. So coming back, classical mechanics is very good in the sense that if you know the position of the particle and you know the momentum of the particle, then you can describe the system with 100% certainty. Okay, so what that means is that given the position and the velocity times the mass, because momentum is equal to mass times velocity, if you know these two variables, then you can say that I can describe the system fully. Okay, so it turns out that um, yes, so you can describe the system fully with these two variables, but also you need a set of constants. Okay, so with the help of two variables x and p, and with the help of some set of constants like mass, gravitational constant, I don't know, the spring constant k, and etc., so on. If you're given these constants and you know the position and the momentum, you can describe a classical system with 100% certainty. So we'll see why that doesn't apply to quantum mechanics. Okay, in the quantum world, things aren't like this. So let's start off with some discussions that led to quantum mechanics. So basically, it all started with a debate, okay? And the debate was on the nature of light. So specifically, the debate focused on the physical nature of light. Okay, so is light a particle or is light a wave? So there were many experiments that suggested that light was a particle. Other experiments suggested that light was a wave. So you can see that it's very confusing that you do an experiment once and it turns out okay that light behaves like a particle. Then someone else does another experiment that's similar and it turns out light behaves like a wave. So it was very perplexing to scientists, very confusing to scientists that what is the true nature of light? Okay? So people like Newton thought that light was a particle, and Newton thought light was a particle because if you if you shine light on a prism, it turns out that light splits into its 7 colors that we described by Webb-Goyer: violet, indigo, blue, and so on. So Newton thought that light was made up of particles, and the prism sorts these particles based on wavelengths, and that's why we see colors. That was Newton's logic. Other scientists thought that light was a wave because of certain experiments they did. And I would say that one of the most famous persons was Maxwell. He came up with his electromagnetic theory, and he came up with a set of equations that basically pointed towards the fact that light is a wave. Okay, so before Maxwell, people took Newton's word because he was a very smart guy. But when Maxwell came with his theory, then it casts doubt onto the nature of light. Then people were like, nope, light is a wave, it's not a particle. But lo and behold, the debate didn't settle over there. Okay, the debate still continued because of other experiments which gave rather confusing results. So we're going to start off with one of those experiments, and hopefully this experiment lays the foundation for our discussion of quantum mechanics. And the experiment I'm going to discuss is Young's double slit experiment. Okay, so I chose this specific experiment because it's going to help us it's going to help us define a particle and define a wave. Okay, and then based on those definitions we're going to correlate it to light, and then we'll see what's the nature of light. So here's how the experiment goes. Okay, so the experiment is that you have some sort of slit, and by slit I mean a hole that's on a surface. It's a hole that you put, and through that hole you can send light, you can send particles through that hole, whatever you want. And then on the other side of the slit you have some detection device. Okay, and that detection device is going to detect every time a particle or a wave lands there. It can do so by changing colors, it can do so by just having a pattern on it. So somehow that detection device is going to measure particles and waves coming onto this screen over here. So it turns out that when we send a particle through here, the pattern formed on the detection screen is different. When we send light through the slit, then the pattern formed on the detection device is also different. So basically the idea here is that if you can identify the pattern that particles make on the detection screen, and you can identify the pattern that waves make on the detection screen, then basically you can send anything through that slit, and then you can see what kind of pattern it makes on the screen, and then you can relate it to the pattern made by particles or waves, and then you can decide, and then or you can figure out exactly what the nature of the thing was that you sent through the slit, whether it was a particle or a wave. So first things first, let's kind of discuss what a wave is and what a particle is. So a particle is something that we all know what it is. A book is a particle, a golf ball is a particle, you're a particle. Particles are localized in space, okay? What that means is they are defined very well in space. If you have a golf ball, you know where the golf ball starts, you know where the golf ball ends, you can hold it in your hand, and it is very well defined. Waves, on the other hand, are delocalized. So they're very spread out. If you guys remember, or if you've taken some math courses, then you could think of a sine or a cos wave. Okay, so the wave's position is very uncertain. You don't know, where the wave is. So that's what I mean by delocalized. It's spread out in space, and it doesn't make sense to classify the wave based on its distance. There's something else that we use to classify a wave, and that's called the wavelength. But anyways, the point of this discussion is that what happens when I send particles through the slit? What happens when I send waves through the slit? Okay, so we assume that if we have one slit and we send a particle, so for example, let's say you're standing on the other side of this slit and you start throwing balls. You start throwing balls, let's say you start throwing tennis balls. So it turns out that, sometimes the ball you throw will land right at the center. Sometimes you'll throw the ball, and because you don't have the best aim in the world, the ball might go somewhere on the periphery or the edge. Other times it might go along this direction. So it turns out that the pattern you're going to see on the screen is something like this. Okay? So it means that in this edge, the probability of finding the ball is very low, and if you get towards the center, then you're more likely to find the ball there, right? So we can say that this is the intensity graph of the ball or the particle. The intensity graph looks something like this if we send particles through a single slit. And I know I called it the double slit experiment, but I want to start off with a simple case by looking at one slit, and then we'll go on about looking at two slits. So similarly, now, if I have one slit and I have some sort of selection device, or detection device on the other side. Now what happens if I send waves? So waves look something like this. And how you can do this is you can have you can have a big bath of water, and you can place slits over into the water vertically, and then you can put your finger in and out of the water, and you can create waves, and then these waves will propagate through the slit, and then they'll end up onto the other side, onto the detector. So it turns out that the pattern for waves in a single split, it is very dissimilar to a particle. It looks something like this. So instead of the previous case in a particle, we saw that there was one peak, and that was the place where you would find the most amount of particles. In waves, you get this squiggly kind of pattern, right? So there's some sort of maximum here, there's some sort of minimum over here, there's some maximum here, there's a very big maximum over here, and so on. So why do we see this pattern? Why isn't it like particles? Why do we have this kind of weird pattern being formed? And the reason for that is because waves interfere with each other, okay? So you should know that waves can interfere with each other constructively, which means that they add up. The net result is adding. For example, if the waves are in phase, that means their crest and their troughs align. So the crest and the trough are basically fancy ways of describing the maxima and the minima. So if you add up these waves and they're in phase, then it turns out that you're going to get a bigger wave as a net result. However, now let's assume that you have waves that are not in phase. Okay, so one of these waves is like this and the other wave is like this. Okay, so there's some sort of phase difference between these two waves. As you can see, this is a minima here, but on the other wave, you have a maxima. Similarly, here we have a maxima, but on the other side we have a minima. So it turns out that this is called destructive interference, that the waves will cancel out, and you probably will get something like this, like the waves cancel out, their amplitudes cancel out. So you basically get a destructive effect. Okay, so basically when there's a destructive effect, we see minimas, and where there is a constructive effect, we see these maximas. Okay, so it might not, you might think that how is one wave interfering with itself, right? It's like there's only one wave, so how is it interfering with itself? Well, you kind of think of it like this. So the scientist who explained this single slit pattern for waves was this very smart guy named Huygens, and he said that think of the fact that every part on the wave is capable of forming more waves. Okay, so when this wave propagates through this slit, then you say that there are many waves that are coming out because of the different points on that wave. Each point on the wave is capable of generating different more waves. Okay, so then you would get some sort of pattern like this. So then you would see that points like this, there's destruction, there's a destructive effect, and in other points like this, there's a constructive effect. So basically, when there's a constructive effect, you see a maxima. Where there's a destructive effect, you see a minima. So this is not to scale, but hopefully you get the idea. All right. So with this, I'm gonna leave this video for you guys to kind of start thinking about the different patterns that waves form and the different patterns that particles form. And in the next video, we'll start discussing the double slit experiment. Now I want to move on to the two double slit experiment. So in the last video, we looked at a single slit experiment. We looked at the pattern formed when we send particles through a single slit and when we send waves through a single slit. But now let's make things a little bit more interesting. And now let's consider the double slit experiment. So this is the Young's double slit experiment, and first we'll do it for a particle and then we'll do it for a wave. Okay, so for a particle, this is what's going to happen. So you have two slits. Okay, I'm gonna say that the first one is S1 and the second one is S2. And then you have your detection device onto the other side. So if you're standing here and you start throwing particles, then like I said, some of your aims will be very good and you'll land right in the center of the slit. But then other times your aim will not be so good and you might land somewhere on the periphery, like this. Okay, similarly for the second slit, sometimes you will land right in the center and other times you will land somewhere along the sides. But it's important noticing that this area over here, there will be no detection because there's a barrier present. So obviously you won't really find anything in this area. So the intensity plot for this looks something like this. So you have some intensity due to the first slit, then we have a barrier, so there's no intensity there, and then we have the intensity because of the second slit. So our pattern looks like this for the double slit experiment when you throw particles. Okay, don't confuse this to be a wave pattern. It just shows that you have some pattern. So if I divide this into two parts, it's basically like you have one intensity curve for one slit and then you have a second intensity curve for the second slit, and then you basically have no intensity over here because there's a barrier. So this is how it would look like if you started throwing particles through the slits. If electrons or light behaved like a particle, then if we started throwing it through a double slit, then we would see this pattern. Okay? Now let's move on and let's see how waves behave. Now here's where things get a little bit more interesting. So we have the same experimental setup. We have S1, we have S2, we have our detection device onto the other side, and let's say we start generating waves. There's many ways you can generate waves, but really that shouldn't be the focus of our discussion. But if you really want to know, what you can do is you can, like I mentioned previously, you can have a big water bath. You can place the slits in horizontally, or sorry, vertically in that water bath, and you can dip your finger in and out, creating waves, and then those waves can pass through the slits. If that's hard for you to imagine, then you can also say that we can pass lasers through these two slits, and that lasers are also waves, so then you would also see a wave pattern emerging. Okay, so here's what's happening. So you send a wave through the first slit, and you send a wave through the second slit, and you get a wave like this coming out, and then you get a wave like this coming out. So it turns out that the pattern you will see is similar to the one you saw in the single slit for a wave, but it's just that now the maxima and the minimas will be bigger, because now instead of having one wave, you're having two waves. Okay, so the pattern will look something like this. The amplitudes would be bigger just because of the fact that now you're sending in more waves, and so then there'd be a greater constructive effect, and there would be, of course, that destructive effect as well. So the point here is that you would see some light fringes over here, because that's where the wave is landing. But then you would see some dark fringes over here, because there's nothing over there, right? The waves are destructively interacting, so they don't even hit that spot. Similarly, you would see some light spots here, and then you would see some dark spot here. Then you would see something that's very, very light over here, and then so on. So this is the pattern you would see for waves, and then this is the pattern you would see for particles. So now that we've defined a wave and a particle, and we have some experiment that helps us distinguish between the two, now we're going to start doing something interesting. Now we're going to start sending electrons through the single slit and or basically we'll send electrons through the double slit, and we'll see what happens. Okay, so I want to show you an animation of the double slit experiment, just so that you see it happening, and maybe then it'll make a little bit more sense. So here's how the animation looks like. You're sending waves from a source. If you look at the left side, so the leftmost side in this picture, you're sending waves. So as we progress to the right side, we send waves through one slit, and then we send it through two slits. Okay, so when we send it through two slits, then we see that the waves interact with each other, and the points where the waves intersect, that's where they're destroying each other. And then there would be points when the troughs of the waves align, and then you would see light spots. And the places where the waves intersect, that's where you would see dark spots. Okay, so based on this, we basically have an idea of what waves look like and what particles look like. Now let's do something interesting. Let's do the same experiment with electrons. So of course, back in the days when Young came up with this experiment, I think it was in the 1800s, technology wasn't very advanced at that time. So I think electrons weren't even discovered then. So you really couldn't do this experiment, right? Because you didn't even know electrons existed, and you couldn't do this experiment with light either, because they didn't have the technology. So come 19th century, we were able to send electrons through the double slit, and then we were able to see what the nature of electrons was, and it was actually very confusing. The results were very confusing. So if we send an electron through one slit, let's see what happens. So let's say I have some source of electrons here, then I have a detector over here, and I start sending electrons. Okay, and let's say I observe what happens over here. So I start sending electrons and I observe what happens here, and I notice that the pattern looks like that of a particle. Okay, interesting, very nice. So is an electron a particle? Well, scientists said that let's confirm this with the double slit experiment. And then we'll see if it's a particle or a wave, right? So right now our bet is on the fact that electrons are particles. And we've really thought of them as particles, I'm sure, until now. If you've thought of electrons, I'm sure at some point in your life you would have thought them to be like little balls. But let's see what reality tells us. Now let's do the same experiment, but rather than having one slit, we have two slits. So now what happens? So you have a source that's sending out electrons, you have one slit, you have the second slit, and we start sending electrons. So it turns out that we would see an electron land here, maybe then an electron would land here, maybe then it would land here, maybe here, and so on. And if we did this experiment for, let's say, 30 minutes, 40 minutes, or an hour, then we would see some pattern emerging. And the pattern we see looks something like this. Okay, so basically it's the same pattern we saw for waves. So that there's some light spots, okay, and that there are some dark spots. So I'm gonna represent the dark spots with this color, with this orange color, and I'm gonna spell and the blue represents the light spots. Okay. So now it's very confusing. How is it that you send something through one slit and it behaves like a particle, and then you send something through the second slit, or now you send something with two slits and it starts behaving like a wave? That's very weird, okay? So maybe the electrons are interfering with each other, okay? Maybe that's why we're seeing this pattern. So then technology developed to such an extent that we could send one electron at a time. If we send one electron at a time, then obviously that means that the electrons aren't interfering with each other, right? If we're sending one at a time, then they're not interfering with each other. But guess what the pattern is after 30, 40, 50 minutes? Yes, it looks like this. So it means that inherently electrons have a wave nature as well. So this is what I mean, that this experiment should lay the basic this experiment is where we should start off our discussion on quantum mechanics with, because it has very, very interesting results. So the question now was, is electron a wave or is it a particle? What do we do? How do we decide this? So the answer was given by someone called de Broglie, I'm sorry, I don't know how to pronounce his name. So he's the guy who came up with the answer to this problem. He was actually a prince, and he came up with the answer to this problem. But before we discuss Broglie's answer, let's discuss some points from this double slit experiment. So remember, I said that if we send one electron at a time, then what would happen is we would eliminate the chance of interference. But the surprising thing is that, you know, sometimes the electron would land here, and I'm representing by green. Sometimes it might land here, other times it might land here, other times it might land here. But the thing is, we can't predict where it would land. So we can never really predict where the electron will land with certainty. And that was really confusing to scientists, because all of the experiments we do, we know the results of the experiment. We can hypothesize, and based on theory we can guess the results of the experiment. For this, we can't guess the behavior of one electron, but we can guess the behavior of a group of electrons. Okay, so that's one perplexing idea, that you can't determine position of electron with certainty or confidence. What you can do is you can predict it with probabilities. You can say that okay, there's a there's a likely chance, there's a bigger chance that the electron will land somewhere here than there is a chance that the electron will land somewhere over here. So you can only talk of things in terms of probabilities, and that is also one of the very confusing results of this experiment. So what I want to do now is I want to show you the diffraction pattern made by electrons, and I'll do that through an animation. So this is actually how it looks like when a laser is sent through the single slit. But I'm actually looking for the electron, and here it is. So the electron, it comes, and you can't predict where it will land on the screen, but over time, so as you'll see, a pattern starts to emerge where you have dark fringes and you have red areas and then you have black areas. Okay, so this is the double slit experiment. This is the result of the double slit experiment. To sum up things, in single slit experiment, the electron behaves like a particle. In double slit experiment, the electron behaves like a wave. So what do you do? What's the nature of electrons? We'll discuss this in the next video. And now I want to finish off with one more peculiar behavior about these electrons. So remember I said that you cannot predict where the electron lands, and in fact you can't even predict which slit the electron goes through. It's impossible. You can't predict that if an electron will go through this slit or if an electron will go through this slit. So now let's say that you're trying to be clever, and you place your eye onto this slit S2, and you say that okay, I'm going to look at this slit, and every time an electron passes by, I'm going to know that it went through slit 2, and then I'll know where it lands on the detector. And of course, if an electron lands somewhere that is far away from this second slit, then I can say that it came from the first slit. Okay? Okay, this is theoretically, it seems very convenient that if I started looking at one of the slits, then perhaps I can know which slit the electron passes through. The peculiar thing here is that once you look at which slit the electron is passing through, it starts behaving like this, like it was going through a single slit. It starts taking on the behavior of a particle. So how is it that the electron knows that you're looking at it and then it takes on particle-like behavior? That is also a very intriguing question that scientists could not figure out. That how is it that if you monitor which slit the electron goes through, it takes on the behavior of a particle? And then if you're not monitoring which slit the electron is going through, then it behaves like a wave. So this is something I want you to think about, and then hopefully it gets you a little bit interested about the weirdness of quantum mechanics, and it gives you a desire to study it. So with this, we'll start things off in the next video. In the last video, we looked at the double slit experiment involving electrons, and we saw some peculiar behavior, some strange behavior of these electrons. We saw that if these electrons went through one slit, then they behaved like particles, and they took on this shape that is the shape of a particle that lands on the detector. And then we said that if there are two slits, then it behaves like a wave. Then, to eliminate the possibility that this wave was created due to interference, we sent one electron at a time, but we still saw the same pattern. Then another thing is that we could never predict where the electron is going to land with 100% certainty. We could guess based on chances, but we could never predict it with 100% certainty. Einstein didn't like this idea at all. And I'm sure many of you have heard this quote by Einstein. He said that, God doesn't play dice. God doesn't work on probabilities. God works deterministically, like how it should be in the classical world. And then someone told Einstein, don't tell God what to do. Right? So nature is how nature is. We have to understand it, but we have to understand it according to reality, right? So if reality is telling us that we cannot predict it with 100% certainty, then that is what it is. And I can tell you that this experiment has been repeated many times. And the results have always been the same. So it has nothing to do with experimental error. It has nothing to do with the fact that that perhaps our experiments are not going right. It has nothing to do with that. It is an inherent part of nature. Okay, now moving on. So this had a peculiar effect of showing us that electrons could behave like waves and they could behave like particles. So now the question is, what's the true nature of electrons? What's the true nature of light? Because they both give the same results in this experiment. Okay, so I'm going to give a timeline of all the experiments that were done that led us to this point, and then I'll explain the issue and I'll solve it, and I'll tell you which scientist came up with a solution for this problem. So we're going to start off with Newton. Newton, from his prism experiment, he said that light is a particle. Then Huygens came. And actually, Huygens actually said this before Newton, but we'll just discuss him now. He said that he said that light. So sometimes I'm going to be talking about light, sometimes I'm going to be talking about electrons. So don't get confused by that, but just know that they're interchangeable, right? That the nature of light is very much the same as the nature of an electron. So we'll be sometimes talking about light, sometimes we'll be talking about electrons. As you know, light is made up of particles called photons, right? So you can think of that as the analog to electrons that we've been discussing. So anyways, Huygens said that light is a wave because, and this weird sign means because. So Huygens thought that light was a wave because he saw an interference pattern. Okay. Then came along Maxwell, and he too said that light is a wave. And I'm going to represent a wave like this because I'm too tired of writing it out. So Maxwell said that light is a wave. Then came Einstein. And Einstein did the photoelectric effect. And basically he concluded that light is a particle. So what the photoelectric effect is, I'll briefly explain it. You have some sort of metal, and the photoelectric effect was actually discovered accidentally. So it was very curious. People couldn't explain the photoelectric effect until Einstein came about and he explained it. But this is what the photoelectric effect is. If you shine some light with an appropriate energy, then what it does is it hits the surface of the metal and it ejects an electron out with some kinetic energy K. So that is very weird. How is it that we have light that's basically throwing out an electron from the metal? How is it that light, something that you see all around you, how is it able to knock out an electron? Well, Einstein said that it is only possible if we thought of light as having as being made up of distinct particles, and he named them photons, and he said that these interact with these electrons and they result in the removal of electrons. So there's one electron removed per photon. Okay, so based on this, Einstein thought that, okay, light is a particle. And then the last person I'm going to talk about is Compton. And then Compton gave further support of the idea that yes, electrons are particles. Compton actually wanted to prove Einstein wrong. So he did experiments, he did many experiments, and it turns out that in the end he realized that actually Einstein was right, that light did have a particle nature to it. So what Compton did is he said that if light comes with some energy initial, or let's say some initial wavelength, we won't talk about energy yet, so let's say light comes with some initial wavelength and that light hits an electron, then it turns out that the collision causes a change in wavelength of the light. Okay, so basically it kind of shows, like, if you're playing pool, you basically like, I'm sure many of you have played the game billiards. So Compton said that this is kind of like that situation in which one billiard ball hits the other billiard ball, and then the other billiard ball goes flying somewhere else. So he said that this change in wavelength can be thought of like that, but the only way you can think of light being like a billiard ball and an electron being like a billiard ball is if you assume that they're particles. Because surely light, like if we think of light in its traditional sense, it's not, it doesn't seem like a billiard ball. But Compton said that for this experimental result to be explained, we have to consider light to be like a billiard ball. So as you can see, there are many experiments that were giving contradicting results. So it was very perplexing for the scientists until Mr. de Broglie came, or De Broglie. I'm really sorry, I don't know how to pronounce his name. It's been very long since I've been taking this courses, but I've never really learned to say his name because everyone really pronounces it differently. So if someone knows the correct pronunciation, please type it in the comment section. So Mr. Broglie was actually he was actually from the royal family. So this is extraneous, but he was from the royal family, and this guy was actually in the humanities before, and then he switched on to physics. And when he was writing his PhD thesis, he wrote his PhD thesis on the principle of wave particle duality. So Mr. Broglie said that, hey, instead of thinking of the fact that, is light or electrons a particle or a wave, how about we think that they have both characteristics, in the sense that, objects, let's just say objects are wave and particle like, depending on the situation. So there's no classical analog to this. In the real world, you don't see anything that has a wave and a particle-like nature. So it's very hard to imagine wave-particle duality. So it's something you kind of have to take as an axiom, or something that's just, it comes out naturally from observations. So it is slightly hard to imagine this. But here, think of it like this. Think of the fact that you're in a dark room and there's a car in the dark room, but you don't know it's a car. So you start feeling your way around, and then you touch the tire, and you're like, oh, okay, maybe this is made out of plastic, whatever object this is. Then you go and then you touch the light, the headlight of the car, and then you're like, oh, this is kind of like glass. So then you say, okay, so then you say that, oh, this object is a glass, and this object is a plastic as well. But when you turn on the lights, you see that it's actually a car. So it's kind of like that scientists were in the dark, and they were feeling around light, but they didn't really get the whole picture. They got parts of the picture. But then when the light turned on, quote unquote, when Mr. de Broglie came, he turned on the light, and then scientists were like, oh, it has both properties. There's many pictures. You could look at pictures online that have a dual nature. They basically, in one picture, there's two images. There's one picture, but there's two images. Depending on the perspective you take, you see one of those two images. So you can look that up online. I won't really go through that here, but it hopefully helps illustrate the idea of duality, the aspect that things have dual nature sometimes. So what we'll do is we'll come up with a simple derivation that de Broglie came up with, to explain this idea. So he started off with this. He said, okay, well, if objects have a wave particle duality, then their energy as a wave should equal to their energy as a particle. So as we know, the energy of a wave is h nu, and the energy of a particle is mc squared. Okay, we can rewrite nu as c over lambda, because that's the relation. Nu is equal to c over lambda, or c is equal to nu times lambda. So this is the relation anyways. So this c cancels out with one of the c's in the c squared, and what you can do is you can solve for lambda, and what you get is you get h over mc, and this is the formula for the wavelength of a particle. Okay, so this is a restrictive case where I say that the velocity of this object is equal to the speed of light. But in life, particles don't travel at the speed of light. So I'll make a slight modification to this formula and rewrite it as h over mv. And as you know, mv is equal to momentum. So I can also rewrite lambda as h over p. So basically, you're relating the two properties of a wave and a particle. Remember, I told you in the start that particles can be described by their position and their momentum, and waves are primarily described by their wavelength. So this relation shows us mathematically wave-particle duality. So you might be asking, why don't we see waves in our scale, right? Why don't I look like a wave? Why don't you look like a wave? And the answer for that is this. So the mass for large objects like us is very high. So if you divide this number by a very, very high number on the bottom, then it turns out that lambda will give us a small value, right? Think about it. If you divide 10 to the minus 34 by a very large number, you divide it by a very large number and you get a small number in return. So the idea, I can even show you easier math. Let's say 20 divided by 100. Compare that to 20 divided by 1,000, and so on. So you see, if you increase this number, the overall number decreases. So it turns out that since our mass is very large, the wavelengths we see are very, very small. They're almost negligible. So we don't see a wave associated with you or me or anyone. But in the world of atoms and electrons, then the mass is very small in value. So mass is small in value, so you have a relatively large wavelength that can be observed. So with this, I want to end the video on this wave particle nature that de Broglie came up with, and in the next video we'll discuss some implications this has. Last time we left off with the de Broglie relationship, and that relationship was lambda is equal to h over momentum, or h over mv. And we said that since massive particles had large masses, the lambda was small. And this is called an inverse relationship. So an inverse relationship just means that if one thing is increasing, the other thing decreases. If one variable is increasing, the other variable decreases. Okay? So for massive particles, the wavelength is very small. It's almost negligible. You don't see it. For small particles, the wavelength is large, and therefore it is observable. Okay. Now we will talk something about the Heisenberg's uncertainty principle. So it actually follows along quite nicely from the de Broglie relationship, and we'll see how so. Okay. So let us assume that we have some wave along the x-axis that's described like this. Okay. The wavelength for this wave is this. So the wavelength is basically when you complete one pattern. Okay. So I start at the middle of a maxima here, I go down, then I come up, and then I end at the second maxima. So basically this is one wavelength, okay? And then these wavelengths make up the whole wave. Okay, so a wave, some wave has an associated momentum, and we will say that momentum can be described in a particle-like fashion, and we'll describe it like this. And it has some momentum and it has some wavelength. Here, lambda is very well defined, right? You know what lambda is based on this picture. So therefore, since you know lambda, therefore you also know momentum. So this momentum is very well defined. But what's the position of this particle or this wave? What's the position? So let's say I want to find the position at y is equal to 1. And say that's this point over here. So is the particle here? Is the particle here? If I were to extend this wave, okay, like this, is the particle here? So you can imagine that, we know the momentum very well, but what we don't know now is the position of the particle. Okay? Now, let's say that we combine many waves to get something called a wave packet. If you guys have done introductory physics courses, wave packets are introduced when it comes to sound, or harmonic oscillators. In that physics block, they teach something about wave packets. But what, for our understanding, we're just going to use the basic idea of a wave packet, and that is you combine many waves to get a well-defined wave in terms of bounds. Okay, what I mean by that is you can have something like this. So you can have a wave that is clearly in these bounds. Okay, so outside of these bounds A and B, the wave takes on a value of 0, and inside these bounds there's some value of the wave. Now my question to you is, what's the lambda? Well, as you can see, you don't know the wavelength here at all. right? What's the wavelength? You can't figure it out. So you might not know the wavelength here, but what you do know is you know the position a little bit better. So now the position of the particle is somewhere between A and B, right? In this example, it was somewhere along minus infinity to positive infinity. It could have been anywhere. But here, it's confined in the range of A and B. So the idea here is that if you know the momentum, then you're losing out on the position. If you know the position, you're losing out on the momentum. And this is the Heisenberg's uncertainty principle. So Heisenberg's uncertainty principle says that the uncertainty in momentum times the uncertainty in position, or in the uncertainty in position times the uncertainty in momentum, is always greater to or equal to h over 4 pi. Okay? Or basically to the order of 10 to the minus 34, because if you divide h by 4 pi, I mean, it's not a huge difference, right? Like h is equal to 6.636 times 10 to the minus 34. You divide that by a number close to 20, and it's not going to make a huge difference to the whole number. So the point is that um, this relationship has to be greater than or equal to minus 34. So basically what it means is if you know one of these, if it has a high value, then to maintain this relationship, the other one has to have a low value. And this is the uncertainty principle that Heisenberg came up with. And this is in very, very stark contrast to classical mechanics, in where if you knew the position and the momentum, then basically you know those things with 100%. Like I was saying, in the very first video, I gave a silly example that if you and your friend are playing catch and you throw the ball and it lands in your friend's hand, then you know for a fact that it is in your friend's hand. But if you throw the ball, but it had a quantum nature to it, you could throw it towards your friend, but it might land somewhere. Let's say you're in Las Vegas, and then next thing you know, the ball is somewhere in Nevada, or it's somewhere in Ohio, or it's somewhere in Canada. So that is kind of the uncertainty principle, that if you know um, one of these variables, then you don't really know the other variable. So it turns out that classical mechanical system or quantum mechanical systems are not well defined based on x and p. They're not well defined on these two things. They must be defined by some other variable. And we will talk about that variable later on. Okay? So I want to finish off this video by saying that psi x, or I mean sigma x, is inversely proportional to sigma p. So that's the whole idea of the uncertainty principle, that if you increase the certainty in one thing, then you lose out on the certainty in the second thing. So you can never know these two things with 100% certainty, and this is the Heisenberg's uncertainty principle. In order to understand quantum mechanics and the wave nature of matter, it's pretty important that we start understanding the wave nature of matter from a classical perspective. So first, let's see how classical physicists described waves, and then based on that, it'll really help us understand how quantum mechanics people, they describe waves. So I'll begin off with an example. So let us consider a wave that we make by a rope. Pretend that we have a rope or a string, that I tie one end of the rope here along x is equal to 0. I call this point x is equal to 0. And then on the other end, I tie it along, let's say, a second wall, and I call that x is equal to L. So I have some sort of boundary set up, and in between that boundary, I have a wave. So for terminology's sake, let's find out all the variables we have. I have an x variable, which is basically the distance along the horizontal axis. And then I have some variable u, and that's basically the height at any point along the x-axis. And then I also have this variable t, time, and it just means that this wave can change as time goes on. So u depends on two variables, x and t, right? The value of u is different here at this value of x, it's different here at this value of x, and so forth. And as time goes on, we also assume that u changes value as well. So another thing you should know is that when u is a maximum, that means the biggest height that the string can take or the wave can take, it's called the amplitude of the wave. And basically it's just u max. So it turns out that u x of t, it satisfies some sort of differential equation. It satisfies this differential equation. So it's really not important for us to kind of understand where I got this equation from. You all are taking quantum chemistry, so we'll try to keep a lot of the derivations to a minimum. We'll just try to cover the important parts. So all we need to know is that the height of this wave or this rope or this string, it satisfies this linear partial differential equation. Now, some important things to understand here is that this is a partial differential equation. What that means is u depends on x and t, right? So here, u here is only dependent on x and u here is only dependent on t. So it's a partial differential equation because u is supposed to depend on x and t, but here I only have u being dependent on x and here I have it dependent on t, so we're taking something called a partial differential. If there was only one variable that u depended on, then I would just call it an ordinary differential equation. So to signify that this is a partial differential equation, I put this weird looking d. So whenever you see that d, it just means that u depends on more variables than what you see down here. Okay? So the thing is that we don't really like dealing with partial differential equations, so somehow we have to make this into an ordinary differential equation. And we'll talk about that soon enough. Now, another thing we should talk about is that u is the dependent variable. Its value depends on the values of x and t, right? So x and t here are independent variables. You see x and t can change, and depending on that, u changes as well. So we also, whenever we have partial differential equations, it's very important to set up something called a boundary condition. Without boundary conditions, it's very hard to solve partial differential equations. So boundary conditions are basically how the physical system is set up. When you do problems like this many times, boundary conditions will become very easy for you to identify. So here the boundary condition is this. I have one boundary at x is equal to 0 and I have another boundary at x is equal to L. The important thing is at both of these points 0 and L, the value of u is equal to 0. That means the string has 0 height. And it doesn't matter what value t takes on. If I'm standing in this system for 10 years, 100 years, or a billion years, I've set up the system in this manner that at those two ends, u will always be 0. Now moving on, it turns out that we can solve this equation for u x of t by a special method, and it's called separation of variables. Now, it's very important that you follow along and you try to understand this method, because all throughout quantum mechanics we'll be using separation of variables quite a bit. So it's important that we understand what this method is all about. Now, the key step for separation of variables is this. We assume that ux of t can be separated or factorized into two components. It can be factorized into a component that just depends on one variable, which in our case is x, and then it can also be factorized into another, which just depends on t. So if I multiply these two components together, I get the whole function that I'm interested in, ux of t. So most of the times when we have partial differential equations, we're going to have to solve it one by one. We're going to have to solve it one independent variable at a time, because if you do it two independent variables at a time, it becomes almost impossible to solve the equation. So this is really important, and it might seem daunting at first, but don't worry. Once you do this one or two times, this isn't really that hard. Okay, so now I know that ux of t can be written as two factors multiplied together, x of x and t of t. So I'm going to go ahead and I'm going to substitute that into my parent equation, which is this. When I do that, right, I get this and this. So all I did is I substituted u with the two factors. Now, in this part of the derivative only depends on x. That means we can treat t like a constant and we can pull it out. Similarly, here the derivative only depends on t. So then I can bring out x and treat it like kind of a constant here, because d here we assume that it only depends on one of the variables, so the other I can just pull out. So that's what I just did in this step. For this one, I say that t kind of acts like a constant, so I pull it out and I'm left with only x terms. And here I say that x acts like a constant because this derivative only acts on t. Now, something interesting happened. When I did this derivative, it only depends on x, this derivative only depends on t, so this is something that I call an ordinary differential equation. So this is ordinary, this is the differential that we're used to seeing, right? This looks like a normal d that we're used to seeing. Okay, so far so good, nothing too hard. All I said is u can be factorized into two components, one that depends on one variable x and the other that depends on the other variable t, and then I went and I substituted u with that. Okay, so now you know the drill, we have to collect like terms. So when I do that, I can bring this x to this side and it goes on the bottom of the equation, and this t I can bring it to the other side and it goes on the bottom with t, or I mean sorry, with v. Okay, so when I do that, I'm left with this equation, 1 over x of x times this differential is equal to this guy times that differential. Now here's the catch. X and t are both independent variables. That means their value doesn't depend on the value of u, right? Time will continue to go on. It doesn't matter what height the wave takes. Time will continue to go on its own pace. So t and x are kind of like independent variables. But the important thing is, for both of these equations to be equal, right? For both of them to be equal to each other, as this suggests, they have to equal to the same number. Okay, so I'm going to say that they're both equal to some number k, that both of these equations end up equaling to some number k. It could be 10, 20, 1, 2, doesn't matter what it is. It could even be a negative number, but I'm just saying that it equals to some number k. When I do that, I can separate both of the equations, okay? I can say that this guy, it's equal to k, and similarly, the t terms are also equal to k. And k is called the separation constant, and we have to find it out. So now I'm going to rewrite the equations so that I get everything on one side. What I'm going to do is I'm going to move this x along with k, and I'm going to move this v squared times t along with k, and then I'm going to bring them all to one side. So you can figure out that math yourself. It's really not that hard. All I did is I cross multiplied and then I brought it to the other side. So I'm left with this equation and this equation. Okay? So these are called ordinary differential equations with constant coefficients. This constant coefficient, negative k and negative kv squared, they're constants. They don't change their values. Okay, so that makes our life a lot easier. From the first equation, I can find out x of x. From the second equation, I can find out t of t. And then once I have those two quantities, I can multiply them to get u x of t, and that's what I'm looking for. So hopefully you're following along and you realize that really the whole issue is that we have to solve these equations one by one for each variable. Now let's find k. So if we can find k, then we can easily find x of x and t of t. It turns out that k can have three values, right? It can either be 0, k can be a positive number, which means it's greater than 0, right? Or it could be some negative number that's less than 0. Before we move on and talk about solving the classical wave equation further, it's really important that we start talking about complex numbers. So before we go on, I'm going to start talking to you about the first major math concept that we'll go through. It turns out that if you think about it, there's three major classes of numbers. The first class is something we're all so used to seeing, and that's the real numbers. So the real numbers are anything that runs on the number line, like -3, -2, so forth, up until positive infinity. Pi, e, these are also real numbers, and we're used to seeing them. Now I'm going to introduce something different that we haven't seen, and it's the imaginary number. So we're taught in high school that basically you can take the square root of a negative number. And it turns out that's true. You can take the square root of a negative number and get a real number as an answer. It doesn't make sense like that. So we have to introduce a new idea, and that idea is that if you take the square root of a negative number, you end up with something called an imaginary number, okay? And the simplest imaginary number there is, it's the square root of -1. So that's the simplest imaginary number you have out there. Now, if I combine a real number with an imaginary number, if I add them or if I subtract them, then I get something called a complex number. So a complex number is basically just a real number plus an imaginary number. Like, for example, 5, which is a real number, plus square root of a -1, which is an imaginary number. So I call this the complex number, and I represent it by this weird looking C. Okay? Now the question is, of course, what's an imaginary number? It's kind of like the imaginary friend you had in your childhood. It helps you in hard times when you don't have friends, but the sad thing is it only exists in your mind. So imaginary numbers are kind of like that. We basically use them to help us out with physics and stuff like that, but they don't really exist, right? So it's just a tool that we invented to make our math easier. Imaginary numbers are not pointless. They have very important uses. As this course progresses on, you'll see those uses soon enough. For now, just try to understand what an imaginary number is. Okay, it's really not that hard. Um, an imaginary number, by definition, is basically the square root of -1. So the square root of -1, I give it a special symbol I to represent that it's an imaginary number. So whatever number this guy is, it's an imaginary number. So it turns out that I can have lots of imaginary numbers. I can have 1 times square root of -1. I can have 2 times square root of -1, 3 times square root of -1. In fact, I can also have, square root of -1 times pi, which would turn out to be pi I, right? So if I is equal to square root of -1, then it follows that if I square I, then I can get rid of this square root and I'm left with -1. So the important point to keep in mind is that the square of an imaginary number always gives you a real number. So imaginary numbers on their own might not be helpful, but if you square them, then it's extremely useful for us, okay? So they're kind of like a secret code. You don't really get what you want unless you square it. Now let's talk about complex numbers. So we talked about real numbers, we talked about imaginary numbers, now we talk about complex numbers. Complex numbers are complex because they have a real and an imaginary part. So we can write any complex number z, I'll give it a special name, as x plus iy. So it turns out that the real part of z is x. It'll be a real number like 5, 6, 7, 2, 4, -1, and so on. And then you'll have some sort of imaginary part of z that's stuck with an I, and I'm going to call that y. So x is the real part of z, and y here is the imaginary part of z. So let's do a tiny, easy example. If z is 5 plus square root of -36, well, how do I rewrite this complex number a little bit simpler? Well, you can recall that square root of 36, this part, I'm going to go ahead and I'm going to rewrite it as -1 times 36. So this 36 turns out to be 6. The square root of 36 is 6. And the square root of -1 is I. So this is where I get the 6i from. And I put a positive negative there because whenever you take the square root of a number, then you're left with a positive or a negative number. And that just goes back to basic math. If you square any number, positive or negative, you always get a positive answer, right? So if you square root any number, it could have come from a positive number or a negative number. So that's why I put a positive negative there, okay? So let's not get lost in semantics right now, but the important thing to recognize here is that this is a complex number in the form of 5 plus minus 6i. The real part of this number is 5 and the imaginary part of this number is 6 because it's associated with the I. Now here we're more interested in finding out things like how do you add and subtract complex numbers, right? So let's go ahead and find this out. If I want to add this complex number with this complex number, then this is what I do. z1 plus z2 is 5 plus 3i plus 5 plus 9i. So think of the real numbers as apples, and I really can't draw apples, but here's something that looks like an apple. And think of the imaginary numbers like oranges. So you can add apples and apples, you can add oranges and oranges, but you can't add an apple and an orange. What's 5 apples plus 3 oranges? Doesn't make sense, right? So I'm going to go ahead and I'm going to add the so-called apples or the real numbers. So 5 plus 5 is 10, and then I'm going to go ahead and add the oranges. So 3i plus 9i turns out to be 12i. So it's just simple addition that we've been seeing so often. You kind of treat the I like some sort of variable, and then you go ahead and you do the math. Treat I like x. Like just treat it like any normal algebraic equation where I can be replaced with x, and then do the math that you already know how to do. Now, the next question is, z1 is this number over here, z2 is this number over here. How do I subtract them? So the question asks, what's z2 minus z1? So the order is kind of switched around, but that doesn't really make a difference. So the question is asking us, what's 5 minus 10i, which is z2, minus 6 plus 2i, which is z1. So remember, the negative sign distributes inside, and therefore I'm left with 5 minus 10i minus 6 minus 2i. And then I just do the simple algebraic math that I'm so used to doing. So I go ahead and I add and subtract the like terms. So 5 minus 6 turns out to be negative 1. And minus 10i minus 2i just turns out to be negative 12i, right? So this is the answer. Now another question is, how do I multiply two complex numbers? For this, you have to keep in mind that I squared is equal to negative 1. We talked about this recently, right? If the square root of negative 1 is equal to I, then I squared is simply just equal to minus 1. Now, this is z1, this is z2, and we're asked what's z1 multiplied by z2, okay? So, 5 minus I multiplied by 2 minus 3i. So again, it goes back to algebra. We know how to do this. We multiply the 5 with the 2 first, then we multiply the 5 with the negative 3i, I'm sorry. Then we go ahead and we multiply the negative I with the 2, and then we go ahead and we multiply the negative I with the negative 3i. So let's see what we get. 5 times 2 is 10. 5 times negative 3i is negative 15i. Minus I multiplied by 2 is simply minus 2i. And then minus I multiplied by minus 3i is this. So what's minus minus? It's positive. Okay? So then I'm going to be left with 3i squared. Positive 3i squared. So I'm going to go ahead and simplify this a little bit more, and I get 10 minus 17i. Now remember, what is I squared? It's equal to negative 1. So 3 multiplied by negative 1 is minus 3. And I'm left with 7 minus 17i as my answer. So last time we left off at how do we multiply, add and subtract complex numbers, and today we'll pick off at how do we divide complex numbers. So the whole recipe for dividing complex numbers is pretty easy. All you have to do to divide complex numbers is to multiply the fraction with the complex conjugate of the denominator. So the only new thing you're learning here is what's a complex conjugate. So if I multiply this fraction by the complex conjugate, we'll see what that is in a second, but right now let's see what the math is going on at. So if I multiply this fraction with the complex conjugate of the denominator, I also have to divide the same by the complex conjugate of the denominator to maintain neutrality. Okay, so it's like if 5 is equal to 5, well, if I multiply this side by 2 and divide this side by 2, then the answer is still going to be 5, right? So if I want to maintain that neutrality in the equation, if I multiply the equation with something, I also have to divide it if I don't want to change the equation in any form. Um, Moving on, what's a complex conjugate? Basically, a complex conjugate is just, it's the complex number, but with the opposite sign in front of the I. So if a complex number can be written as x plus iy, then the complex conjugate of that number is simply x minus iy. If this number had a negative here, then of course the complex conjugate would have a positive, okay? Another important thing to remember here is that if you multiply a complex number with the complex conjugate, you always get a real number. So I'll do an example and we'll figure out what that means in a second, but this is really important to understand. A complex number multiplied by its complex conjugate always gives a real number. So here I have z1 is equal to 2 plus I and z2 is equal to I plus 2i. 1 plus 2i, I'm sorry. So what's the complex conjugate of z1? Well, like I said, it's just the same number but with the opposite sign in front of I. So it's pretty simple. So there's that. For z2, the complex conjugate is this number. So now the question is asking us what's z1 divided by z2? Well, remember, the recipe here tells me if I want to divide these two numbers, I have to multiply it by the complex conjugate of the denominator. Let me just switch this a little bit. I'm going to go z2 divided by z1. Okay? So in this case, my recipe is z2 divided by z1. And then if I want to get the answer, I have to go z1 complex conjugate, and then I also have to divide by the complex conjugate of z1. Let's see where this takes us. So z2 is 1 plus 2i. z1 is 2 plus I. So then I have to multiply this by the complex conjugate of the denominator, and I get 2 minus I on the top and 2 minus I on the bottom. So if I FOIL this out, then I get 2 minus I plus 4i minus 2i squared. Okay? For the denominator, I'm left with 4 minus 2i plus 2, right? And then minus I squared. Okay, let's see where that leads us. 4 minus 2i. I'm sorry, this should be a plus 2i, right? Because I multiplied by 2 is positive 2i. So on the top, I'm left with 2 minus 2i squared plus 3i. And on the bottom, I'm left with 4. These two numbers cancel out, minus I squared. Okay? So I squared, remember, can be written as negative 1. So on the top, I'm left with 2 plus 2 plus 3i. And on the bottom, I'm left with 4 plus 1. Okay? So I'm left with 4 plus 3i divided by 5 as my answer. Now remember, a complex conjugate multiplied by the complex number always gives a real number as an answer, and here the real number that I got is 5. Okay, so this is how you divide complex conjugates. I think dividing two complex numbers is probably the hardest thing you'll see because you have to introduce this idea of a complex conjugate. But if you do this problems like 1 or 2 times, it's really not that hard. Now let's move on. So it's so far we've talked about complex numbers, but I told you that they're composed of an imaginary part. So you might be wondering, do complex numbers actually have any usefulness in math and physics? And the answer is yes, they do. And Euler's formula really helps us connect imaginary and complex numbers with real numbers, okay? So basically, I know that any complex number can be written as z is equal to x plus iy. Then Euler came along and he said that any imaginary number can also be written as a sum of a cos and a sine term. Okay, we'll see how he got that and we'll see what this means in a second. But really, you can convert anything that has an imaginary number into real numbers as well. And we're going to see that in a second right now, how you do it. So if I look at z, it has a real part, which is x, and then it has an imaginary part, which is y. So a lot of values of x and y will satisfy this equation. In fact, there might even be an infinite number of values of x and y that satisfy this equation. So I can go ahead and I can plot all of these x's and all of these y's on a graph. And if I do that, well, then I get some sort of straight line that looks like this. So this is called a complex plane, right? This plane that you see, this piece of paper, on your piece of paper, if you look directly down at it and you see kind of this plane, this is called the complex plane because there's a real part and there's an imaginary part here. So let's see what happens. Let's pick any point on this graph, and I'll pick this point over here. It has an x value and a y value. Okay, the y value is this guy, so that means this whole height is y, and this whole base is x. Okay, and then I'm gonna call the hypotenuse r. So this is a right angle triangle with a height of y, a base of x, and a hypotenuse of r, and of course there's some theta associated with it as well. Okay. So let's bring back grade 10 mathematics SOHCAHTOA. Sine theta can be written as opposite over hypotenuse. The opposite is y, right? It's the opposite to this angle. And the hypotenuse is r. So I'm going to rearrange that to solve for y, and I get this equation. Similarly, cos can be written as adjacent divided by hypotenuse. That's what this means, adjacent divided by hypotenuse. Adjacent, it's the side that's adjacent to the angle theta. So the side that's adjacent, or meaning that touches angle theta, is x. So then I have x over r, and I can solve this for x and I get this. Okay, now I have some value, a real value for y, and I have a real value for x. It turns out that the hypotenuse r can also be written according to Pythagorean theorem as x squared plus y squared, and then I square root this, right? Because one side is x, the other is y, and then I can use the Pythagorean theorem to get r. If I want to find this theta, then I use TOA, or tan, which is opposite over adjacent. Okay, so then theta is simply inverse or second tan y divided by x. Okay, so inverse tan y divided by x, or arctan as they call it. It's on your calculator, you press second tan and then you'll get theta. Okay, so this is how you find theta. So I know how to get theta, I know how to get y, I know how to get x so far. Going back to z is equal to x plus iy, I can go ahead and replace the value of x with the new x I found out, and I can go ahead and replace the value of y with the new y that I found out. Okay, so you can see that this r is a common value in this whole equation. So I can factor that r out. If I factor an r from the first part, all I'm left with is a cos theta. If I factor r from the second part, I'm left with I sine theta. Okay, so I'm left with r cos theta plus I sine theta. If you go back, you'll see that Euler's formula basically is that EI theta is equal to cos theta plus I sine theta. So I can rewrite this part as EI theta. Remember, Euler's formula says that EI theta is equal to cos theta plus I sine theta. So I can replace this part with e to the exponent I theta. Okay? So, therefore, z can be written as r multiplied by e to the exponent I theta. Well, if z can be written as that, the complex conjugate of z turns out to be just r e to the exponent negative I theta. Remember, a complex conjugate is just the same quantity but with an opposite sign in front of I. So now, what happens if I multiply z with its complex conjugate? Well, I know that I'm going to get some real number. Okay? Well, let's do this. If I multiply them together, well, these two bases of the exponent I theta are the same. Remember, we're taught in exponents that when the base of an exponent is the same and they're being multiplied, then I can go ahead and add the exponents. If I add I theta to negative I theta, I'm left with 0. So e to the exponent 0 is just equal to 1. In fact, anything to the exponent 0 is equal to 1. So z multiplied by its complex conjugate equals to r squared. So r squared is just equal to z multiplied by its complex conjugate, or simply it's equal to the square root, r is equal to the square root of z multiplied by its complex conjugate. Now, it turns out that I can also find the magnitude of z by simply square rooting r, okay? You can see how the reverse works. If I want to solve for these z's, just the magnitude, I don't care about the signs. If I don't care about the signs, then I'm just left with z squared, okay? So then z is equal to r to the exponent 1/2, or it's just the square root of r. So this is really important as well. Now let's do a practice problem to bring this all together. So if z is equal to 1 plus I, then what's the value of r? What's the magnitude of z? And what's the phase angle theta? I forgot to tell you one thing, and that's this form is called the polar form. Okay? So it's the polar form because there's I theta, there's I, and there's sine theta. Because of this angular dependence, this is the polar form, okay? So this is a very kind of opposite of what you're used to seeing. We're used to seeing the Cartesian version of this, right? In all the classes that we've done so far, probably you're used to seeing Cartesian coordinates, but now you're going to have to start getting used to something called polar coordinates, and these are coordinates that involve angles, okay? So remember, this is the Cartesian form, and this here is the polar form. So sometimes they'll ask you, okay, they might tell you if z is equal to this, what's the polar form? And if they're asking for the polar form, they're basically just asking you to put this into this form. Okay, so we're just going to do a simple example for now. We'll do more complex examples later if you guys want me to do them. So if z is equal to I plus 1 plus I, then what's the value of r, what's the magnitude of z, and what's the phase angle theta? The first thing is probably the easiest thing to find here is r. So remember, z multiplied by its complex conjugate is just r squared, right? So that means 1 plus I, and then I take the complex conjugate, which is 1 minus I, that's going to give me r squared, okay? So I'm left with 1 minus I plus I, and then minus I squared. So these two cancel out, And remember, I squared is equal to -1. So then I'm left with 1 minus -1, or basically 2. So R is equal to 2. Now, that shouldn't be too hard to calculate. So we know what R is. Now remember, what's the magnitude of Z? The magnitude of Z, it's basically the square root of R, or it's the square root of 2. So remember, a square root can be written as a fraction, okay? So if I have any exponent in the form of a over b, the top part represents an exponent. Here the exponent is just 1. The bottom part, so the exponent here is 1. The bottom part here represents what root are you talking about? Are you talking about the square root as we are in here? If this was a cube root, then I'd have a 3 over here and so forth. Okay, so this is kind of important to know that I can write exponents in this form. Okay, exponent divided by the root. We're gonna do this quite often, so try to understand it right now. So we got the value of R, we got the value of Z, and now the question, of course, is that what's the value of theta? Well, theta is given by tan theta y divided by x. So in this example, what we'll do is, we know that z is equal to x plus I y. If I compare this with what I'm given, it's quite obvious that x is equal to 1 and y is also equal to 1, right? This I is being multiplied with a 1. So both y and x are just equal to 1. So sometimes you're going to have to do this guesswork. They'll give you z is equal to 1 plus I something, or 1 plus 2i. Then you'll figure out that, okay, 1 that corresponds to x and the 2 corresponds to y. So this is something you're going to have to figure out, but it's really not that hard. So if tan theta is equal to 1, then if I'm looking for theta, then all I do is I go second tan on my calculator, I put a 1 here, right? And if your calculator is in degree modes, you'll get 45 degrees. If your calculator is in radian modes, you'll get pi over 4 radians. Okay, so with this, we're done complex numbers. So we'll move on by discussing the classical wave equation in a lot more detail. It's really important that you understand complex numbers because we'll be using them a lot. I hope this video helped. Good luck. Last time we derived the classical wave equation up until here. We converted a partial differential equation to an ordinary differential equation with constant coefficients. So I'll remind you that the constant coefficients were this guy and this guy, right? They're constant and they're coefficients of x of x and t of t. Before moving on, let's remember something, or I'll bring up an important point, and that's whenever you have differential equations in the same form, like here, they're both constant coefficient, they both have constant coefficients, and they're both ordinary differential equations, and they're both equal to 0, so they're in the same form. Whenever you have differential equations in the same form, then their solutions are also similar. So x of x and t of t better have similar solutions if this equation is mathematically valid. And that's just, it follows along from ordinary algebra, right? If you have x plus 2p is equal to 5 and y plus 2q is equal to 6, if I solve them for x and y, I get answers that are in the same form, right? Both of these numbers are just being subtracted from each other. So the important thing is when you have two equations in the same form, their answers are also in the same form. So before I can solve equation 1 and 2, I need to know the value of k. I just have way too many unknowns, right? So first I gotta see what the value of k is, and then I can go ahead solving x of x and t of t. So let's imagine that k can have three possible values, and we'll go on about this with the process of elimination. We'll try out one, then we'll try out the other, and then the third, and we'll see which one gives us a useful answer. So the first case is the most easiest case, and that's k is just equal to 0. The second case is that maybe k is some positive number, and the third case is maybe k is some negative number. Okay, but if I want to put those in the language of math, right? How do I represent a positive number in the language of math? Well, you can just say that k is equal to beta squared. It's any number multiplied by itself, right? Because that would always give you a positive answer. So a negative number, or I mean, sorry, any positive number can be written as a square term, because any negative number multiplied by itself is a positive number. Any positive number multiplied by itself is also a positive number. So in the language of math, this is how you represent positive numbers. How do I represent negative numbers in the language of math? Well, I know what a positive number is in the language of math. It's just beta squared, alpha squared, gamma squared, a squared, any number squared. If I want to make that into a negative number, I simply multiply the result with -1. So now let's go and look at the easiest case, that k is equal to 0. If k is equal to 0, I go ahead and I put 0 over here and 0 over here. So if I do that, well, this guy is going to become 0. And similarly, this guy is going to become 0, because any number multiplied by 0 is just 0. So that leaves me with a very simple equation, right? It leaves me with this second order differential equation and this second order differential equation. Now, if I want to solve these second order differential equations, I have to integrate. And that would give me answers in terms of x of x and t of t. I don't want answers in terms of dx of x over dx of x over dx and dx t of t over dt. I just want answers in terms of x of x and t of t. So somehow I gotta get rid of the d's. And how do I do that? Well, you integrate this. And the question is, how many times do you integrate this? You have to integrate it twice, right? Because there's two differential terms and they're to the order of 2. Now, this should be covered in a introductory calculus course, or an introductory multivariable calculus course. So I'm assuming that most of you know how to do these easy calculus questions. But if you don't, just leave a comment, and I'll go over integration in a separate math video. So if I integrate this once, remember, if I integrate one side, I also have to integrate the other. So if I integrate this just once, then on the left side, instead of having a second order differential, now I just have a first order differential. The integration of 0 always gives you some constant a1. Well, the integration of 0, it doesn't give you any x term, but it leaves you with a constant, and I'll call that constant a1 for x, and I'll call that constant a2 for t. But that still doesn't give me my answer. I still have those d's, so I gotta integrate it one more time to get rid of the d's, okay? If I integrate it one more time, then on the left side I'm left with x of x and t of t. That's something that I want. Okay, the integration of a1, you can imagine that there's an x to the exponent 0 over there, because anything to the exponent 0 is just 1. So if I integrate that, there's going to be a +1 over here, and there's going to be a 1 over on the bottom, and then you introduce a integration constant b1. So that's how I'm left with a1x plus b1, and on the other side I'm left with a2t plus b2. I put the subscripts as 1 and 2 to differentiate that one is for x and the other is for t. So now I have an answer in terms of x and t. Again, remember, in the start I said that because these differential equations are in the same form, their answers are also in the same form. And you can see here, yeah, the answers are in the same form. So the question is this our answer? Are we done? Well, not quite yet, because I don't know the value of a and b, right? I just have way too many unknowns. So first I have to do something about this a and b. In order to find the values of a and be, I have to go back into my system and I have to look at the boundary conditions. Okay, so remember the boundary conditions simply said that when x is equal to 0 and x is equal to L, that means we're at the two extreme ends of the system, the value of u will be equal to 0. So that means at this point ux of t, which I wrote as x of x times t of t, it's equal to 0. And here, that same value of u is also equal to 0 at this point. So when x is equal to L and when x is equal to 0, the whole u term is equal to 0. So I did that mathematically. I just wrote that here, that these are our boundary conditions, right? At 0 and at L, u is equal to 0. Okay. So that means that the x component at these parts is also equal to 0, right? There might be some time, the time's still going on. Time isn't equal to 0 at the two ends, right? Time might be equal to 0 on the first end, but along the other side it's not equal to 0. So that leaves us with the fact that x of x is 0 at the two extremes. So I can go ahead and I can use this information and put it into here and solve for A1 and B1. So when x is equal to 0, then this whole thing is also equal to 0. When x is equal to L, then of course this whole thing is also equal to 0. So look at the first equation, right? When x is equal to 0, this thing becomes 0. That means B1 is equal to 0. Now I know what B1 is. So now instead of putting x, let's put L, right? If I'm looking for A1. So if I put L here, then I know that B1 is 0 because I just found that out. That means that A1 is also equal to 0 because L isn't equal to 0. L is some number. L is probably like 5 meters, 10 meters. How far away are you from 0? So L can't be 0. That means A is equal to 0. This is telling us that A and B are both 0. So if I go back into my parent equation, that means A1 is 0, B1 is 0, and that just goes on to show that for any value of x, for any value of small x, x of x is equal to 0. And if I put that back into ux of t, that means for any value of x, u is also equal to 0. But that doesn't make sense. Mathematically, it makes sense. But physically, it doesn't make sense. Physically, we know that in between the boundaries, u has some height. So this type of solution, we call it a trivial solution. The word trivial means insignificant. So it's mathematically correct, but physically it's not correct. So this is kind of the tricky part about differential equations, that you sometimes have to solve them in a trial and error way, but usually the math guides you properly, okay? So the first thing is that k is equal to 0 is not an acceptable solution. It's mathematically okay, but physically it's not okay. That means case 1 is out of the question. Okay, so the take-home message is this, that just because the solution is mathematically valid, it doesn't mean that it's also physically valid. Okay, so that's something you have to logic out yourself. So before we move on into the second case, I just want to bring into light a mathematical fact that we'll use quite often throughout this course. So please pay attention to this and try to memorize this. And the fact is this: if I have any general differential equation in the form of this, so if I have a second order differential equation, right, and then I have constant coefficients, right? If I have a second order differential equation and I have constant coefficients and the other side is equal to 0, so if I have an equation in this form, the solution of a and a will always be in this form, e to the exponent alpha a. Okay, had this been an x, then you would have had an x here. If this was a y, you would have had a y here, and so forth. The important thing to know is whenever you have a differential equation with constant coefficients and it's equal to 0, the answer, the solution to this differential equation will always be in the form e to the exponent alpha a, and alpha must be determined mathematically. But that's really not the hard part. Alpha is pretty easy to determine. So again, the key take-home message is that if you have constant coefficients and the answer is equal to 0, or I mean the equation is equal to 0, the solution to that differential equation is always in the form e to the exponent alpha a, where alpha must be determined mathematically. Now moving on, let's try to understand this from an example point of view. So say we have a differential equation in this form. I have d squared second order differential equation with respect to y, then I have a first order differential with respect to y, and then I just have 2y, and this is all equal to 0. So first ask yourself, does this have constant coefficients? Well, the coefficient over here is 1, and that's a constant. The coefficient over here is 3, that's a constant. The coefficient over here is 2, and that is also a constant. So yeah, it's constant coefficients. The second question, is this equal to 0? Yeah, it is equal to 0. So that means the solution for this is in the form y is equal to e alpha x. So I know that that's what the solution. So now recall that any differential equation in this form, the solution, if it satisfies two conditions, and that's if it has constant coefficients and if it's equal to 0 on the other side, which this equation does, then the solution is always in this form. It's in the form y of x is equal to e to the exponent alpha x, and like I said, alpha must be determined. So I'm going to go ahead and I'm going to plug this equation to my parent equation, and I'm going to get d squared e to the exponent alpha x divided by dx squared minus 3d e to the exponent alpha x divided by dx squared plus 2 e to the exponent alpha x is equal to 0. So if I differentiate this, the first term twice, well, I'm going to be left with, so remember, the differential of an exponent is always this. You end up with the same term, but then you use the chain rule, and then you end up taking the derivative of the exponent. The derivative of the exponent is just alpha, because alpha is a constant. X disappears, and I'm left with alpha. So when I do the first differential, I'm gonna be left with this. Sorry. If I do the first differentiation, I'm going to be left with this. For this guy, all I'm left with is 3 alpha e to the exponent alpha x plus 2 e to the exponent alpha x is equal to 0. So now I'm left with alpha squared e to the exponent alpha x minus 3 alpha e alpha x, or oopsies, e to the exponent alpha x plus 2 e to the exponent alpha x again is equal to 0. So here, e to the exponent alpha x is a common factor, so I'm going to pull it out, and I'm going to be left with alpha squared minus 3 alpha plus 2 is equal to 0. So this ends up going to the other side, and it becomes 0. So I'm left with alpha squared minus 3 alpha plus 2. If I factor this, I'm left with alpha minus 2 and alpha minus 1. So if you don't know how to factor, leave a comment and I'll do a video explaining how to factor polynomials. I expect that most of you know how to do this, but if some of you don't, then you can leave a comment section and I'll do a video explaining how to factor polynomials. So basically here alpha is equal to 2 and here alpha is equal to 1. So if alpha has two values, what does that mean? It means that y of x also has two values. It also has two solutions, not just one, but two. One solution is e to the exponent 2x, and the other exponent is e to the exponent just x. So you have two exponents in this form. Okay, so this is the answer why the solution for this differential equation is this. So this differential equation has two solutions. So basically, if I had three values of alpha, it would have three solutions. If I had four values of alpha, then there would be four solutions for y. Here I have two values of alpha, so there's two solutions to y. And I'm gonna leave this video off. I'm gonna end this video by giving you a problem that you can solve yourselves. And here's the problem. It turns out that if y has two solutions, right? E to the exponent alpha x and e to the exponent, e to the exponent x and e to the exponent 2x, then it turns out that any linear combination of these two will also give you a solution. So what I mean by that is y of x, if I took any linear combination of the first solution, multiplied by any constant, doesn't matter, plus I take the second solution and then I add a constant to it, then whatever answer I get will also be a solution. So that means that C1 multiplied by e to the exponent x plus C2 multiplied by e to the exponent 2x is also a solution to this. So it might seem really weird that, oh, how is it that, I'm adding both of the solutions and somehow I'm also getting a solution. Well, it's true, it happens, and if you look at the graph, you can mathematically and graphically verify this as well. But I challenge you to assume that this is the solution for this equation. So put this back into this equation and see if you end up getting if you end up solving the equation. So the answer is it will solve the equation as well. If you put y is equal to e to the exponent x, or y is equal to e to the exponent 2x, or if you put y is equal to c1 e to the exponent x plus c2 e to the exponent 2x, if you put any three of these solutions back into the parent equation, you will verify that these are indeed solutions for this differential equation. So this is kind of your homework. Try to see and try to verify whether this linear combination is actually a solution or not. And this is going to give rise to a very peculiar property of waves and then consequently of quantum mechanics as well. So this little formula is actually quite peculiar and also quite interesting. So verify this for yourself. Try to follow the math along until here. Do all of these derivations yourself because the math only gets more intense, I would say. So try to do this. It's not too hard so far, but see if you can verify this equation with this linear combination. So with that, I end this video. Good luck. So last time we finished off with this idea that if you have any differential equation that has constant coefficients and it's equal to 0, then it has a solution in the form e to the exponent alpha x, and alpha must be determined. And if you have a second order differential, you'll have two solutions. If you have a third order differential, you have three solutions, and so on. But the important thing is that if f of x has two or more solutions, then any linear combination of these solutions is also a solution to the parent equation. So remember, our parent equation was a differential equation in this form. So any differential equation in this form has a solution in the form of y is equal to e to the exponent alpha x. But the most important point to remember here is that this isn't the most general solution. The most general solution is actually a linear combination of all of the solutions y of x has. So here, if this is a second order differential, you'll get two solutions, and the most general solution will be a linear combination of both of the solutions, okay? So the C1 and C2, they're actually integration constants, and we're getting a little technical here. How I derived this equation was by telling you that, okay, e to the exponent of x is a solution. But if you take higher level math and you're used to multivariable calculus, and you can solve this equation without breaking it up or knowing the solution, then you'll actually derive this most general solution as an answer, and C1 and C2 will be your integration constants. But we're not focused more on the math part of it. We are just focused on getting to the answer and trying to see what the solution is to the classical wave equation. This isn't really a math class. So just understand that these equations have solutions in the form of y is equal to e to the exponent alpha x, but all of those solutions, any linear combination of those solutions is also a solution to y of x, and more importantly, it's a general solution to y of x. So rather than using the individual solutions, when we'll be working with these type of problems, we'll actually be using the linear combination version of this. So moving on, last time we discussed that if k was equal to 0, then it turned out that we didn't really get anything useful. We ended up with something called a trivial solution or an insignificant solution. It was the solution that was mathematically valid, but physically it made no sense. So now we're going to go on to case number 2, and we're going to assume that k is actually a positive number. So k is a positive number. That's something that I say in English. But if I want to represent this mathematically, then I can represent this as this equation over here. So I can rewrite capital K as just small k squared. So remember, any number squared is a positive number. So in the language of math, I can write a positive number as just a square term. Okay, so I'm going to tackle x of x first, and we'll do t of t later. So I know that, okay, capital K is equal to k squared. So I go ahead and I substitute that in place of this k. I'm going to use a different color pen to make this more obvious. Okay, so if I substitute k squared in place of k, I'm left with this form of the equation. Now, you ask yourself two questions. Does this have constant coefficients? And the answer is yes, it does. And the other question you ask yourself is this equal to 0? And that answer is also yes. So any equation that has these two criteria met, then it has a solution in the form of e to the exponent alpha x, where alpha must be determined. So once I know alpha, then I know all of the solutions, and then the most general solution will be a linear combination of those solutions. So moving on, I'm going to replace x of x with its solution, which is e to the exponent alpha x. These three dots that I put over here, they just mean therefore. So it's a shorthand notation. I'll use it a lot, so just get used to it. I go ahead and I substitute x of x with its solution, and I go on and I have to take two derivatives. This is a second order derivative, so I have to take two derivatives of e to the exponent alpha x. Here I don't really need to do anything else. So if I take the first derivative, I'm left with alpha outside, and then I take the derivative again, and then I get alpha squared e to the exponent alpha x minus k squared e to the exponent alpha x. If I go ahead and divide both sides by e to the exponent alpha x, I'm left with alpha squared minus k squared is equal to 0. So therefore, alpha squared is equal to k squared, or alpha is equal to positive negative k. Now, because alpha has two values, that signals that there's two solutions to this equation. Okay, so the first solution is going to be e to the exponent kx, and the second solution is going to be e to the exponent negative kx. But remember, the most general solution is a linear combination of both of these. So it's going to be c1 e to the exponent kx plus c2 e to the exponent negative kx. So this is the most general solution because it incorporates both of the solutions. So I don't have to look at the solutions individually. I actually just put it into one equation and it makes life easier. So we'll be working with this form of the equation, okay? So the more pressing question, is this our answer? Well, let's see. We have to apply our boundary condition and we got to find out what the value of C1 and C2 is. So at our boundaries, x is equal to 0 and x is equal to L, that's that physical system of a string that we had, we know that the x component of U is equal to 0 at both of the boundaries. So I'm going to use this information and I'm going to plug it back into this general equation that I have, and I'm going to try to figure out what C1 and C2 is. So first I put x is equal to 0. I look at one extreme end of our system. And if I do that, I replace x with 0, and well, this is going to become 1 because anything to the exponent 0 is just 1. Similarly, this will become 1, and I'm left with C1 is equal to C2, or C1 is equal to negative C2. Okay, now I go on and look at the second boundary condition, and that's when I'm looking at the other extreme end of the system. When x is equal to L, the x component of U is also equal to 0 at that boundary as well. So I go ahead and replace x with L, so that's where these L's come from, and I say this is equal to 0. I know what C1 is. C1 is just negative C2. So they're both the same numbers, but one of them has the opposite sign. So I go ahead and I replace it. I can factor out the C2. I can factor out the C2 because it's common in both of the terms. And if I do that, I'm left with negative EKL plus e to the exponent negative KL is equal to 0. So that means one of these terms has to equal to 0. Well, C2 can equal to 0. There's nothing preventing C2 from equaling to 0. So actually C2 is equal to 0. But more importantly, why isn't e to the exponent KL plus e to the exponent negative KL equal to 0? Well, the answer is this. They will equal to 0, but not in the interval that we're looking for. If I want this guy to be 0, then L has to approach negative infinity. That means L has to be a really, really tiny negative number, okay? And that would make the first term equal to 0. If I want the second term to equal to 0, then L has to be a really, really big number, because e to the exponent negative, let's say 100 billion, it's going to give me an answer that's like 0.000000001, which is almost equal to 0. But that's not a part of our boundary. L is a constant. L can't be negative infinity or positive infinity. L is just a number like 5 meters, 4 meters. It's just how far off the rope is at the other extreme end. So obviously this E term can't be 0. That leaves us with the fact that C2 is equal to 0. If C2 is equal to 0, then based on this equation, I know that C1 is also equal to 0. If C1 and C2 are equal to 0, then that means x of x is also equal to 0 for all values of x, and that doesn't really mean anything either. It's mathematically okay, the math works out, there's nothing wrong with our math, but physically it's not okay. So this again is our trivial solution. Trivial, the word trivial in English means insignificant, meaning it's okay mathematically, but physically it's insignificant for us. We don't care much about it. So k is not a positive number. That leaves us with the fact that case 2 is also wrong. Case 2 is not the right answer as well. So you better believe that k is actually going to be a negative number. So we'll work out the math in the next video. I hope this helped. Okay, so remember, any differential equation in the form of this that has constant coefficients and is equal to 0 has solutions in the form of e to the exponent alpha x. But remember, the most general form is a linear combination of all of the solutions y of x has, okay? So another thing I want you to recall is from the math lesson that I did, we talked about complex numbers, and I said that any complex number can be written in terms of its real part x and its imaginary part y. So it can be written as this. An imaginary number is simply the square root of -1. So I is equal to the square root of -1. If I square both sides, then I squared turns out to be -1. And I simply is the square root of -1. So another important point here was that if you square an imaginary number, you get a real number as a result. Now another thing I mentioned was Euler's formula, and that was e to the exponent positive negative I theta is just equal to cos theta plus negative plus minus I sine theta. So you can write complex numbers in two ways, and most people will actually work with Euler's formula. And remember, Euler's formula is the polar representation of a complex number, whereas the Z form is the Cartesian representation of a complex number. And like I said, we'll actually be working with polar forms a lot more than Cartesian forms, okay? So moving on from that, let's go back to deriving the classical wave equation, and we're at our last case, and that case is basically assume that k is a negative number. So if k is a negative number, I represent that mathematically by multiplying any positive number k squared with -1, okay? So I'm left with negative k squared here. So recall that our parent equation here is this term, and I'm gonna go ahead and substitute k with negative beta squared this time, not k squared, but I'm just gonna pick some arbitrary symbol beta squared just for the fun of it. And I'm gonna substitute x of x with its solution e to the exponent alpha x. So if I do that, I did the substitution, and now I'm just gonna go ahead and do the derivative of e to the exponent alpha x 2 times, and then I'm gonna try solving the equation for alpha. Okay, so I take the derivative once, I'm left with alpha. These two negative signs cancel out, and I'm left with a positive sign. I do the derivative again, and I'm left with alpha squared e to the exponent alpha x here. These things are unchanged because there's no derivative going on. I divide this whole equation by e to the exponent alpha x, and I'm left with alpha squared plus beta squared is equal to 0. So that means alpha squared is equal to negative beta squared. I'm going to go ahead and I'm going to rewrite that a little bit differently. I'm going to rewrite that as -1 multiplied by beta squared. So I'm going to take the square root on both sides now. So if I take the square root on both sides, on the left hand side I'm left with alpha, and on the right hand side I'm left with positive negative square root of -1 multiplied by the square root of beta squared, okay? So remember, the square root of -1 is simply I, right, by definition. And the square root of beta squared is beta. So alpha here is equal to positive negative I beta. So that leaves me with a solution for x of x in the form e to the exponent I beta x, because alpha here is equal to I beta, and of course e to the exponent negative I beta x. So the general solution, or the most general solution to x of x, is a linear combination of both of these solutions, and you can verify that on your own. I've told you to verify it about 2 times, and if you want, you can do it the 3rd time using this as well. So before I move on and I show you the linear combination, I want to mention that, e to the exponent I beta x is comparable to e to the exponent I theta, where theta is equal to beta x. So, these both look similar. The only difference is instead of having theta, I have beta x. So beta x is just theta, okay? So I just want to mention that. Anyways, let's rewrite it in the most general form, and the most general form that x of x can be written as is a linear combination of both of its solutions, or both of its roots, or whatever you want to call them, or its zeros. So x of x is equal to c1 e to the exponent I beta x plus c2 e to the exponent negative I beta x. So remember, I told you that when we're working with imaginary numbers, we don't really like working in Cartesian coordinates. We like working in polar coordinates. So I'm going to go ahead and use Euler's formula to convert this into its polar representation. Okay, so remember, Euler's formula is e to the exponent positive negative I theta, which is equal to cos theta positive negative I sine theta. Okay, so if there's a positive here, there's going to be a positive here. If there's a negative here, there's going to be a negative here. Okay, so I'm going to rewrite this term and this term with this. So if I rewrite this guy, I get cos beta x plus, right, because there's a positive here, I sine beta x, and beta x is kind of like our theta. And then I'm going to get c2 cos beta x minus, now because there's a minus in front of this I sine beta x. So I'm going to kind of rearrange that by distributing the c's inwards, and I get I distribute the c and I distribute the c over here, I distribute this and I distribute that, and then I collect the like terms. So all the coses are together and all the sine terms are together. Okay, so remember, with the signs, because there's an I in front of the sign, this c is also multiplied by that I. So in this first term, C1 and C2 are kind of, they go together because cos beta x is a factor. So cos beta x gets factored out and I'm left with C1 plus C2. And similarly, IC1 minus IC2 gets factored out and I'm left with sine beta x. So since C1 and C2 are constants, their sum is also a constant, and same thing applies with IC1 minus IC2. So therefore, I'm just going to call C1 plus C2 as A, and IC1 minus IC2 as B. So they're just going to be some numbers. They're going to be some imaginary numbers or some real numbers, but they're just going to be some numbers. So I'm just going to call them A and B instead of, instead of writing out the whole IC1, C2, and so forth. Important thing to note here is that I replace C1 plus C2 with an A and IC1 minus IC2 with a B. So another thing to note is that both of these forms, the Cartesian form and the polar representation, are equivalent. And if you don't believe me, you can go and you can substitute these into the parent equation and you'll get the same answer for both. If you don't understand what I mean by going back and substituting it into the parent equation, leave it into the comment section and I'll do a video explaining it. But I'm pretty sure most of you know what I mean. But if you don't know what I mean, leave a comment and I'll do it ASAP. Okay, now the important question is A cos beta x plus B sine beta x our answer? The last two times we tried this method, I got a trivial solution. So is it right this time? Well, let's apply our boundary conditions and we'll find out. Okay, remember, our boundary condition is that at x is equal to 0 and x is equal to L, the x component of u is also equal to 0. Okay, so if I put 0 here and 0 here, right, then sine of 0, because beta times 0 is 0, so sine of 0 is also equal to 0, so this term disappears. Cos of 0 is actually equal to 1. You can do that on your calculator. So that means A is equal to 0 here. So it doesn't look too good right now, but oh well, we'll move on. So we know that A is equal to 0. We don't know what B is yet. So now let's put our second boundary condition, x is equal to L. When I do that, and I put it into my equation, well, I know that A is equal to 0, so this term disappears. So beta multiplied by sine beta L is equal to 0. Okay, so beta sine beta L is equal to 0. So that means either b is equal to 0. I'm sorry, that was b multiplied by sine beta L. I don't know why I said beta 2 times, but b multiplied by sine beta L is equal to 0. So that means either b is equal to 0 or sine beta L is equal to 0. Well, if b is equal to 0, that gives me another trivial solution. So I'm going to say that, okay, b is equal to 0 is mathematically okay, but it's not okay physically, so I'm going to reject that. So I'm going to say, well, b cannot be equal to 0, because if it was equal to 0, then that would give me a trivial solution. That means sine beta L here must be equal to 0. So if sine beta L is equal to 0, that means sine theta is equal to 0. Because remember, beta L is just equal to 0. Or I mean, beta L is just equal to theta. So sine theta is equal to 0. But the only values of theta that give sine theta is equal to 0 are values such as 0, 180 degrees, 360 degrees, and so forth. Or 0, pi radian, 2 pi radian, 3 pi radian, and so forth. So that means theta is equal to 0, pi, 2 pi, 3 pi, so forth, or beta L, which is also theta, it's also equal to this. So I'm going to say that so generally what I can say is that beta L is just equal to n pi, where n can be 1, 2, 3, 4, and so forth. I reject n is equal to 0 because if n was equal to 0, that would mean that, again, sine is equal to 0, and that would give me a trivial solution. So I'm going to take all of the n values except for 0, okay? Because if I took 0, that would give me another trivial solution. So n cannot be 0, but n can be anything from 1 to positive infinity. So now that I know that beta L is equal to n pi, I can solve for beta. Okay, so remember, beta was like our k. So instead of using k, I use this arbitrary symbol beta. So beta is equal to n pi over L. So finally, we can go back into our parent equation and I can substitute this value of beta into it. So remember, a is equal to 0, so this first term disappears. That means x of x is equal to b sine, instead of beta, I'm going to put n pi over L. And then I have the x from here, okay? So x of x is just equal to b sine n pi x over L for all n greater than or equal to 1. So we finally solved this for x of x. Now we have to solve this for t of t, and we'll pick that up from the next video. I hope this helped. If you have any questions, please leave it in the comment section. Okay, so before we move on to solve for the temporal or time-dependent part of the classical wave equation, let's solve another differential equation that has a slightly different form. So in this differential equation, I have an omega squared. This term, this Greek letter is called omega. So I have an omega squared, and instead of having y as a function of t, I have x as a function of t, meaning that the spatial part, x, depends on time t. So I just made a note here that the independent variable here is t, and the dependent variable is x. So the value of x depends on the value of t. So as time goes on, the value of x changes, okay? So whenever we write independent and dependent variables, we do it in this format. So the dependent variable is outside of the bracket and the independent variable is inside of the bracket. So here we're used to seeing f as a function of x usually. Here things have kind of been modified such that we have x as a function of t. So anyways, we have our parent equation, and we're told that the initial conditions is just a fancy name for boundary conditions, when x at 0, so when t is equal to 0, the value of x is just a, and then the rate of change of x with respect to t is 0 when time is 0. So that means when you just start your stopwatch, when you're looking at the system, like, at 0, the rate of change of x is 0. So this is an ordinary differential equation with constant coefficients, and it's equal to 0. That means, like we've done before, that the solution of x of t has to be in the form e to the exponent alpha t, where alpha must be determined. So the paired equation is, of course, this guy, and we know that the solution is in this form. It's e to the exponent alpha t. So instead of x as a function of t, we're going to substitute its solution in the parent equation. So when I do that, I'm left with this equation. Okay, so I have to take the derivative of e to the exponent alpha t twice, and then everything else is just in algebraic form. There's no need to do anything else to this term. So if I take the derivative of e to the exponent alpha t once, I'm left with e to the exponent alpha t, and then remember, you have to take the derivative of the exponent. That's the chain rule. So the exponent of alpha t is just alpha, because t here is our variable. So this thing stays the same. There's no operators acting on it. If I do the derivative of again, I'm left with alpha squared e to the exponent alpha t. If I divide this whole equation by e to the exponent alpha t, I'm left with alpha squared plus omega squared is equal to 0. If I move omega to the other side, it becomes negative omega squared. So if I square root that, remember the square root of a negative term is I, so and the square root of omega squared is just omega. So I'm left with positive negative I omega. So that means x of t has two solutions, but the most general solution is a linear combination of both of the solutions. So therefore, the most general solution is just C1 e to the exponent positive I omega t plus C2 e to the exponent negative I omega t. So this is the most general form, most general solution. This is the solution we're interested in, and this is the solution we'll try to work with. Omega is a constant. I know the value of I. I know that t is a independent variable, so I'll be given its value usually. So I don't really know what the value of C1 and C2 is. In order to get their values, I have to subject this equation to the boundary conditions or the initial conditions. So remember, the initial conditions, they were these guys, that x at 0 is equal to a, and that the rate of change of x is equal to 0 when time is equal to 0. Okay. So I want to remind you quickly that Euler's formula is a way that helps us convert Cartesian coordinates to polar coordinates. So remember, Euler's formula is this guy over here. And I also said that we'll be working with Euler's formula a lot more than the Cartesian coordinates. So we're going to go ahead and convert this into, the polar representations. So you have to remember that theta here is equal to omega t, because if you draw the parallel, well, I is this guy, therefore omega t must be theta. Okay. So theta is equal to omega t. We know that much. So then I'm going to go ahead and I'm going to convert x of t from its Cartesian coordinates into x of t in its polar coordinates. So instead of this e to the exponent I omega t, I go ahead and I put in Euler's formula. And I do the same thing for the second e term. So remember, the first e term has a positive sign, so that's what I get here. The second e term has a negative sign, and that's what I'm left with over here. I'm going to go ahead and distribute the c inward, and same with c2. So when I do that, I'm going to bring all the cos terms together and all the sine terms together. Okay, so here C1 and C2, they'll add with each other because cos omega t is a factor. It's a common factor, so you can pull that out. So I do the same with the second sine term, and I'm left with this equation over here. So C1 plus C2, it's going to equal to another constant, right? C1 could be 1, C2 could be 2. Well, in the end, 1 plus 2 is 3, so it's also another constant. So I'm going to call that constant, C3. And same for this guy over here. This constant, I'm going to call it C4. There's no point in writing this long equation, all the time. Whenever we can simplify things, we should simplify things to make life easier. So the polar representation is simply C3 cos omega t plus C4 sine omega t. Now remember, the polar representation is the same thing as the Cartesian representation. It's just it's a different way of representing the same thing. Okay, so that's just what I wrote over here, that the Cartesian and the polar representations, they're equivalent. They're just different ways of writing the same thing. Okay. And the important thing is we'll work with polar forms mostly. It makes calculations a lot easier. You might be asking yourself, well, if they're the same thing, why do we have to convert them? The answer is we convert them because subsequent calculations are a lot easier to do. Most of you have worked with cos and sine throughout your high school and university careers, but exponent terms, we're not really that used to solving equations using exponent terms. So it's best to simplify things into a form that you're most used to seeing. Okay, so now we have to find C3 and C4. We'll subject our parent equation, or we'll subject our x of t equation to the boundary conditions, and we'll try to figure out what C3 and C4 is. Well, I know that when x is equal to, when t is equal to 0, then x of t is equal to a. So I'm going to go ahead and I'm going to replace 0 with every t that I find. Okay, so then I do that in this equation, and I know that cos of 0 is just 1. And the sine of 0 is just 0. So that leaves me with the fact that C3 is just equal to A. So now I know what C3 is, it's equal to A. So then I know the second boundary condition, that the rate of change of x with respect to t is equal to 0 when t is equal to 0. So first I have to find the derivative of x with respect to t. Then whenever I see a t, I'm going to substitute it with 0, and then I'm going to say that the whole equation is equal to 0. Now that kind of might seem confusing right now, but here's what I mean. So first I take the derivative with respect to t. Okay, so remember, the derivative of cos theta is just negative sine theta. But here we don't have theta, we have omega t, we have two terms, so we have to use the chain rule. So when I use the chain rule, it's the outside derivative, which is this guy, multiplied by the inside derivative, which is this guy. So the outside derivative is just negative sine omega t. The inside derivative, meaning the derivative inside of the bracket of omega t, is just omega. So that's why I get negative c3 omega sine omega t plus C4. Remember now, the derivative of the outside of sine omega t is just cos omega t. But then the derivative of the inside term is just omega. So that's where I get this term from. Now remember, it's equal to 0 when t is equal to 0. So I'm going to put 0 in place of all of these t's. Remember, sine of 0 is just 0, and the 0 cos of 0 is 1. That means that c4 times omega is equal to 0, or c4 is equal to 0. Okay, so I know that c3 is equal to a and c4 is equal to 0. That means this whole term is equal to 0. Okay, so if you don't understand how to take derivatives involving the chain rule, leave it in the comment section and I'll do a video explaining that as well. So x of t is just equal to a cos omega t, because the other term with the c4, it just becomes 0 because anything multiplied by 0 is equal to 0. So x of t, I know what it is. So that means that the solution to this differential equation, it has a cos term in it, meaning that this solution is kind of like a wave, because remember, cos represents a wave, sine represents a wave. So this is called an oscillatory solution. This solution oscillates in time, meaning it goes up and down, up and down, up and down over time. And it shouldn't be too surprising to you, but I thought I'd write this down, that some differential equations have oscillatory solutions, okay? So if I plot A cos omega t, this is what I get. The amplitude of this wave is A, okay? So this is the amplitude. So that means the height of the wave goes from positive A to negative A, okay? And then it fluctuates with some frequency, right? So it fluctuates with some frequency and some period. I know that this is one wavelength from here till this point over here. This is one wavelength. I know the wavelength. But here's a side note. How do I find the linear frequency if I know the angular frequency omega, right? Um, so what I do is I know that, sorry, this is an angular frequency. This is angular velocity. I don't know what I was thinking. Angular velocity omega. Okay, so the angular speed or angular velocity, I know that, but I want to find out the linear frequency. I want to find out what's the frequency with which this wave repeats itself. Well, let's consider a simple fact. Speed is equal to distance over time. We all know that. So angular speed is equal to angular distance covered over time. But whenever we're talking about, cyclic systems, instead of time, I have something called a period. So consider a circle and imagine that you're standing over here at this point. If you go around the circle once, what's the total distance that you cover in terms of angles? Well, the total distance that you cover in terms of angles is just 360 degrees or 2 pi radian. So that's where the angular distance 2 pi comes from. And the time it takes for you to cross that circle once, it's called a period, right? It's called your period. So t um, is the period of this system, and omega is equal to 2 pi over t. Remember, 1 over t is just equal to the frequency f, but a more scientific way of representing frequency is this fancy Greek symbol nu. Okay? So omega is just equal to 2 pi nu, or 2 pi frequency. So if I know that omega is equal to 2 pi nu, then this frequency, this linear frequency, is simply equal to omega over 2 pi. So this was an aside. I'll do it again when we need it, but I thought that I'd introduce you to this concept right now. We'll need it further on in our discussion of quantum mechanics, but I thought I'd drive this simple relation right now. So the linear frequency is connected to the angular velocity by this relationship. Okay, so we spent a considerable time, a considerable amount of time to figure out what the solution of ux of t is. We said that, ux of t can be separated into its two variables, x and t, and then we can find them to find out u. So we figured out what x of x was in the previous video. But now we're going to find what t of t is, and the good news is the method is entirely the same as x of x, okay? So remember that any differential equation that has constant coefficients and it's equal to 0, the solutions are in the form of e to the exponent alpha x, and you have to find out alpha. But the important thing to note is that the most general solution to these differential equations is a linear combination of all of the solutions which are in the form of e to the exponent alpha x, okay? So in fact, you can have an n number of solutions, And in that case, the solution, the most general solution would look like this, okay? It would just be a linear combination of all of the solutions. You might forget where we're getting these C's, and basically they just come from the fact that, you know, if you're experienced in math, you would be able to solve these differential equations without the guesswork that we incorporated. You know, people who are mathematicians have the tools to solve complex differential equations using very complex methods. And if you knew how to do that and you could solve these differential equations by those methods, you would find out that you would have to integrate these differential equations. And whenever you integrate a differential equation, you end up getting a constant, right? You get an integration constant, and that's what these C's are. They're basically integration constants that you get from solving your differential equation, okay, manually. Now, moving on to find T of t, let's figure out what our parent equation is. And our parent equation was this. It might look a little bit different from the parent equation we had written before. You had a minus k here, but then we said that, k is equal to 0 and k is a positive number. They give us trivial solutions, so the answer is that k is actually equal to negative beta squared, and we figured out the value of beta in our previous video. Beta was actually equal to n pi over L, where L is how much you stretch the string from your origin, okay? So I'm going to rewrite this parent equation a little bit differently. I'm going to collect beta times V, and then I'm going to square that term, so I'm left with this. So the only difference between this equation and this equation and this equation is how I've written beta times V. Now I want you to recall that beta is just equal to n pi over L, okay? And I can also write beta in terms of n. I put an n subscript to tell me that the value of beta depends on n, okay? L here is the constant. Remember, it was just the boundary of my string, okay? I could have a string in any form, but it's just that, L is one boundary and 0 is the other boundary. Now, consider this. I'm going to call beta times V, I'm going to give it a special name, omega. And if you recall, omega is just the angular velocity, okay? If you don't want to remember the derivation I'm about to do, that's up to you, but I recommend that you listen to it so that you can understand why I chose to say that beta times V is equal to omega, okay? You could just remember that beta times V, I'm calling it omega, but here's a more accurate version of why I'm calling it omega, so stick with me. Beta times V is equal to omega. And I said in the previous video that beta here is equal to n pi over L multiplied by velocity V. Now recall that velocity is equal to distance over time, right? Or time here is equal to distance over velocity. I just cross multiplied and I get this. Okay, now here my length is kind of like distance, right? If you started off from here and then you walked all the way up here, you would end up with L, right? So the distance that you cover, from here to here is L. Now, moving on from that, instead of calling it D, I could call it L, okay? So if T can be written as L over V, then 1 over T can be written as V over L, right? I just took the reciprocal of both sides. Okay, now if 1 over T is equal to V over L, that means that this term here is equal to 1 over T. Okay, so if that's equal to 1 over T, then recall that 1 over T is actually equal to frequency f. Okay? So 1 over the period T is just equal to the frequency of a system. So n pi times the frequency is equal to beta times velocity v. n pi frequency is equal to omega. That's just the formula for the angular velocity of any object. Now, you could, so, 2 pi f is what you're used to seeing. But it turns out that that 2 pi f comes from the fact that you do a one circle around, you do one lap around a circle, so that gives you an angle covered of 360 degrees. But you can, when you're revolving around in a circle, you can go around the circle how many ever times you want. So that's why I have an n, which is a more general case, rather than limiting it to 2 pi f. Okay, so you have n pi f or n pi nu, and that is equal to omega n. Now I say that omega here depends on n, how many ever times you go around the circle, right? The velocity is the same, it's just the amount of circles that you cover that's different. So omega here is equal to beta times velocity. So our paired equation can be written as a different way, a slightly different way, and that's, instead of having beta times velocity, I have omega n. So now recall that such an equation has a solution in the form of e to the exponent alpha t. So I'm going to go ahead and I'm going to replace t of t with e to the exponent alpha t. When I do that and I do the math, I get this derivative being this guy, okay? And nothing happens over here. There's no operation going on. So I can divide everything by e to the exponent alpha t. When I do that, this guy disappears, this guy disappears. So alpha squared plus omega n squared is equal to 0, which implies, so then you get something like this. Okay, so then you can square root both sides, and remember, the square root of a negative number is equal to I. The square root of omega n is just equal to omega n. Sorry, the square root of omega n squared is equal to omega n. So alpha is just positive negative I omega n. So remember, this means that you have two solutions, one in the form of I omega n and the other in the form of negative I omega n. But the most general solution is a linear combination of both of these. Okay? So that's where I get this general solution from. Okay, so this is the general solution in Cartesian coordinates. Remember, I always like to work in polar coordinates, so I'm going to use Euler's formula to convert this into polar coordinates. Now recall that Euler's formula is this. In our case, theta, if you compare this guy and this guy, it becomes obvious that theta is just equal to omega n multiplied by t. So I'm going to use this formula, and whenever I see a theta, I'm going to replace it by omega n t. Okay, so that leaves me with the fact that t of t is equal to c3 cos omega n t plus c4 sine omega n t. Okay, we did a derivation like this about 3 times in the previous videos, so you can go back and check them if you don't understand how I got from the Cartesian coordinates to the polar coordinates. But it's done about 3-4 times. If you don't understand, let me know. I'll do it again. Now recall, we had a boundary condition for x of x. We know that the height of the string, we know that the height of the string at the two extremes is 0. So the x component at the two extremes is also 0, but we don't really have any boundary conditions for time, okay? So because I don't have any boundary conditions for time, I'm just going to keep C3 and C4 as my constants. I really don't have any way to figure them out, okay? So C3 and C4 kind of seem awkward. We've been working with A's and B's, so I'm going to replace C3 with a D, and I'm going to replace a C4 with a E, okay? So T of t becomes this form then, where D and E represent the amplitudes of the waves. Now you could leave this with C3 and C4 if you really wanted, but to maintain consistency I put it in the form of D and E. Finally, we can figure out that messy and that sneaky ux of t. It took a long time to figure it out, but now we can find what it is. So remember, when we use the method of separation of variables, we said that ux of t can be written as a multiplication of both of its variables, like this. Okay? So I know what x of x is, I know what t of t is. X of x was equal to this guy, okay? And t of t is equal to this guy. So now I can go ahead and distribute the b inwards, and I'm left with this equation. So all I did is I distributed the b with the d and the e. So, I don't want to always write BD, BE, BD, BE. So instead of those two long names, I'm going to call BD is equal to F, and I'm going to call BE is equal to G. So finally, we know that Ux of t is equal to this long equation over here. But here's where the weird part comes, okay? So omega has a dependency on n. And there's an n over here. So that means that u also has a dependency on n. So u depends on x and t, but it also depends on n. For every different value of n, there's a different value of u. So since u depends on n, since I don't know any boundary conditions for t of t, that means f and g, the amplitude of the wave, also depends on n, right? The amplitude of the wave is just basically, what's the height of the wave. As time goes by, the wave can evolve differently. The wave can look like something like this, or it could look, so at time is equal to 5 seconds, your wave could look like this. Then at time is equal to 200 seconds, your wave may look something like this. At both of these instances, where n has a different value, the height, the amplitude of the wave is also different, okay? So since the amplitude of the wave is different, we say that f and g also depend on n. So I rewrite the equation by putting in n's everywhere to show you that u depends on n and the amplitude depends on n as well. Okay, stay with me for a second. Remember, the solution, the most general solution to any linear differential equation is a combination of all of the solutions, right? Un solves this partial differential equation. If you recall, it's du with respect to dx is equal to 1 over v squared d del squared u over del t squared, okay? So ux of t satisfies this equation, right? But this u is dependent on n. So that means for every n, there's a solution for this equation. Therefore, the most general solution is a linear combination of all of the solutions that correspond to u and x of t, right? So just like how f of x had many different solutions, and the most general solution was a linear combination of all of these solutions. Similarly, ux of t has many solutions that satisfy this equation, but the most general solution is a linear combination of all of these solutions. So that means ux of t can be written simply as u1 plus u2 plus u3 and so forth up until un. I don't write the constants here because I've already counted for those constants with f and g. So it turns out that ux of t happens to be a sum, a linear combination of all of the u and x of t terms, okay? So the most general solution to the classical wave equation is a linear combination of all of these single solutions of un x of t forms. So this is kind of complicated, but if you've been listening and you've been kind of figuring out the pattern to how solutions to a differential equation work, then I guess it shouldn't be all that mind-boggling, right? Um, so this is the most general solution to the classical wave equation, and it's supposedly called a linear superposition of normal modes. So each un x of t corresponds to something called a normal mode. We'll figure out what these normal modes are in the next video. And we'll also figure out what this equation is telling us in the next video. But the point of the matter is whenever you have a string that's bound on two sides, and then you create some disturbance in this string, it will evolve according to this equation, okay? So we'll figure out what that means in the next video, but for now, I hope you figured out how we derive this equation. This is really important, and it builds on very nicely to our discussion of the quantum mechanical wave equation, or the so-called Schrodinger wave equation. So last time, we finally finished off by deriving a solution to the classical wave equation, and the solution looked something like this. So we were left off with the idea that the solution is a linear superposition of normal modes. And I told you that a normal mode was basically each u of xt term. So now we're going to start talking a little bit about what these normal modes are. It's really not important to understand modes, normal modes, and linear superposition states from the classical wave. The classical wave is useful to kind of understand the math behind the phenomena of separation of variables. So the classical wave equation is a really good problem that helps us kind of set up our understanding of how to use separation of variables. But beyond that, the classical wave equation won't be much use to us. We'll be moving on now to the Schrodinger wave equation soon enough. But before we do that, I want to simply explain a little bit about what each un x of t represents. So it turns out that each un x of t represents something called a normal mode of vibration. Basically, each un x of t term represents a different standing wave. So these are the different types of standing waves you can have because of each un x of t term. So when you have u1, basically when n is equal to 1, that was the example we set off with, a string that was tied on two ends, and it went up and down, up and down, up and down, like this guy. So the formula, so if I put n is equal to 1 and I graph that formula, this big formula over here with n is equal to 1, then I would get this image. Similarly, when n is equal to 2, I get this sort of wave being formed. When n is equal to 3, the wave gets bigger and bigger and bigger. When n is equal to 4, the wave continues its pattern of getting bigger and bigger. So the few things I want to point out here is that you need to notice that the ends are tied of each string. So these ends are basically the boundaries of each string. So that's it. These are the boundaries, that they don't have any other name than simply calling them boundaries. But what's important is something called nodes or nodal points. So nodes or nodal points are basically they're points that don't really move in these waves. So because of the presence of these nodal points, or these nodes, I call these waves standing waves because they're standing at the nodes. Everywhere else they're going up and down, up and down, up and down, but at the nodes these are simply standing. They don't have any net movement. So the important question is, what pattern do you see in reference to nodes? When n is equal to 1, I don't have any nodes. I just have two boundaries, but that's not a node. That's just where I tie the string down. So when n is equal to 1, I have 0 nodes. When n is equal to 2, I have one node somewhere over here. So I have one node. When n is equal to 2, or I mean 3, then I have one node somewhere over here, and then I have another node somewhere over here. So the number of nodes is 2 nodes. So I can't really pinpoint the nodes exactly. I guess I'm not that dexterous, but roughly they're somewhere there. When n is equal to 4, then the nodes are here, here, and here, somewhere around there. So 3 nodes. So the point is that the number of nodes is simply n minus 1. And these are the waves that come out from the classical wave equation. You don't have to, you don't, if you find this to be extremely hard and you're getting confused, it's okay. This isn't really going to be, you know, the foundations of quantum mechanics, that if you don't understand this, you're doomed for quantum mechanics. That's not the case. This is just an example that we start off with to kind of make you comfortable with the math associated with quantum mechanics, specifically the math associated with the phenomena of separation of variables. And it's also kind of neat to show you what the formulas give rise to in terms of physical systems. What do these formulas model? Well, these formulas, they give mathematical descriptions of moving waves, in our case, standing waves at nodal points. So this is a standing wave because of the presence of non-changing nodes. So the nodes are at one fixed point. So what's the quantum chemistry connection? What's the quantum physics connection? Well, the idea here is that electrons are simply standing waves around an atom. If you look at these waves, you notice that, well, basically, certain amount of wavelengths fit into each of these waves. Here I have half of a wavelength because one wave looks like this guy, right? So I have one full wavelength here and I have half a wavelength here. So here I have one wavelength. Here I have 1.5 wavelength, and here I have 2 wavelengths. Similarly, like this, atoms essentially have electrons that are standing waves around them. And the key point is that you can only have a fixed number of waves, an integer number of waves around atoms. So if I have an atom, the first shell may be a wave kind of like this. So it has to be a full wave. This doesn't look like a full wave, but it has to be a full integer number of waves, n pi. So that's where something called quantization comes from. So the more n levels you have, the more waves you can fit in. Okay, so essentially the point is, the more waves you have, the more energy you have. So electrons that are further away from the nucleus have more energies because they constitute bigger waves. So that's one connection. The other connection is that covalent bonds, or bonds that are formed from interference of these waves, that's also the result of basically two electrons from different orbitals or same orbitals kind of connecting with each other. So the interference between two electrons give rise to bonds. So electrons are waves. We will learn this soon enough, but it's more important to understand that we will be dealing with electrons as standing waves. So if two electron waves add up, then we get something called a bond, okay? If the two electron waves are in the same phase, so same phase is the key word. So if these are in the same phase, then you get a bond. However, if these electrons are in different phases, okay, um, then what happens is you get a destructive effect and you get something called an antibond. So these antibonds are extremely unstable, and they don't really give rise to stable elements. So this is the quantum chemical connection. Hopefully this helps, and in the next video series we'll start off with, or sorry, in the next few videos we'll discuss probability and statistics. So once we get the math figured out that's involved with probability and statistics, we'll move on to the general principles and the postulates of quantum mechanics. So we'll begin off this video part by discussing the Schrodinger wave equation, and then subsequently we'll also discuss something about a particle which is in a box. So the particle in a box is a really useful problem that kind of helps us lay the foundation of where quantum mechanics is used, and it also introduces quite a few interesting things about quantum mechanics, such as the probabilistic interpretation of the wave function. We'll talk about that later. For now, let's understand what the Schrodinger wave equation is. So say we have an equation f of x is equal to x plus 2. Then we know that the solutions to f of x are in the form of x. In this case, the solution is going to be x is equal to f of x minus 2. Right? So similarly, the Schrodinger wave equation is in this form, and the solutions to the Schrodinger wave equation, they're in the form of psi of x in one dimension. If it was in 2D, then it would be psi of x and y. If it was in 3 dimension, it would be psi of x, y, and z. But the solutions are in the form of psi of x, and if there's no t, that means there's no time dependency with psi, then we say that these solutions are called stationary state wave functions. That means they're stationary, they're not moving in time, and mostly we'll be interested in stationary state wave functions. We'll also learn about time-dependent Schrodinger wave equation, but mostly we'll be interested in the stationary states. So another important thing to mention right now is that the Schrodinger wave equation cannot be derived. When Schrodinger came up with the equation, he probably thought about it, and he fit his equation to the data, which is probably what he did. But the important thing is, just like we can't derive f is equal to ma, we can't derive Schrodinger wave equation anymore. But what we can do is we can show that the Schrodinger wave equation is true, and we can show that the Schrodinger wave equation arises naturally from other equations. So before we do that, let's kind of recap to what de Broglie said. De Broglie said that matter behaves like waves and particles. He said that matter has a dual nature. It has both wave-like properties and particle-like properties. You can't say that matter is a wave or a particle. It's that matter is a wave and a particle. It takes on one behavior depending on the situation that you impose it in. Okay, so that might seem a little bit weird, but it's true. Matter takes on one or the other behavior depending on what experimental conditions and restrictions we impose on it. So since matter behaves like a wave, then we can say that matter waves have a corresponding solution to the classical wave equation. I'll remind you that the classical wave equation is a partial differential equation in this form. So we did a whole video series on the classical wave equation, so if you haven't watched it, I recommend that you watch some of those videos so you understand where we're building on now. So that's the first thing we need to know, that since matter has wave-like properties, it satisfies this weird-looking equation. The second thing we need to know is that since matter has particle-like properties as well, then it must also have an associated total energy, which is composed of a kinetic energy and a potential energy term. So what we'll do is, in order to show that the Schrodinger equation rises naturally from other equations, we'll start off with equation 1. So if we start off with equation 1, let us assume that u x of t can be written as psi of x multiplied by cos omega t. So the important thing is what we're doing is we're doing separation of variables. When we have an equation that's dependent on two variables, what we can do is, in order to solve it, we can say that I can break up the equation into two parts, two components, one which is only dependent on one of the variables, and the other which is only dependent on the other variable. We did a whole video series regarding how to do separation of variables, so I won't go too deep into it. So I hope you can follow along. You might be wondering, why isn't the temporal portion, meaning the part that is concerned with time, why is there no sine term? Well, the reason being is, if time is equal to 0, then sine 0 is also equal to 0, which would mean that the matter wave would disappear at time is equal to 0, and that's not true. Matter waves are present whenever matter exists, so cos 0 does not equal to 0 at t is equal to 0, it equals to 1. So that's why the temporal portion is only dependent on cos and not on sine. So moving on, we'll substitute this into the paired equation, which is this. So I have d, the second part of del, so del to the exponent 2, del is second order. It's first order because it's only one exponent raised, but that's not important right now. We have del squared, then I have psi x multiplied by cos omega t divided by del x squared is equal to 1 over v squared del squared psi of x multiplied by cos omega t divided by dt squared. So before I move on, I want to mention that omega is equal to 2 pi times frequency. Okay, so we did this as well last time. Omega is just the angular velocity. It's equal to 2 pi, meaning one circle multiplied by the regular frequency. That's how you get angular velocity. So in this equation, the derivative only depends on x. So I can pull out the cos omega t term. And I'm left with d squared psi of x divided by dx squared. So now I have an ordinary differential equation because, the derivative only depends on one term, which is x in this case. On the other side, I can go ahead and pull out psi of x, and I'm left with d squared cos omega t divided by dt squared. Now this is also an ordinary differential equation because it only depends on one variable and not two. So moving on, cos omega t multiplied by d squared psi of x divided by dx squared, there's really no change happening over there. But on the other side, the first derivative of cos omega t is simply negative sine multiplied by omega. Then the second, the derivative of sine is cos omega t multiplied by omega. So I'm left with omega squared multiplied by cos omega t divided by dt squared. So here's what happened. So d squared cos omega t divided by dt, that's what I had. Well, the derivative of one derivative turns out to be negative sine omega t, and then I have d over dt, and then I have to take the derivative again, whoops, and there should be an omega here as well, because the rule is inside derivative multiplied by outside derivative. So then I have d sine omega t divided by dt. I take that derivative one more time, and I'm left with minus omega squared cos omega t. So that's how the derivative happened. I'm sure you know how to take the derivative right now. That's not the hard part here. Cos omega t cancels out with cos omega t. And I'm left with d squared psi of x divided by dx squared, which is equal to negative psi of x omega squared And oopsies, I forgot v squared over here, divided by v squared. So what I'm going to do is I'm going to move this term to the other side, and I'm going to be left with d squared psi of x divided by dx squared plus omega squared divided by v squared psi of x, which is equal to 0. Now, I know for a fact that omega is equal to 2 pi times the frequency. I also know that velocity of a matter wave is equal to the lambda times the frequency, right? Because usually c is equal to lambda times frequency, but here, since it's matter, it doesn't go at the speed of light, it travels at a velocity less than the speed of light. So that's why instead of the c, I have to replace it with a v, because we're talking about non-relativistic speeds over here. So I'm going to go ahead and make the substitution. I am left with 2 pi frequency divided by lambda times frequency squared, and nothing happens to psi of x. V cancels out with v, and that leaves me with this equation. So moving on from that, now I have to use my second equation, and my second equation simply tells me that the total energy is equal to kinetic energy plus potential energy, which I'll call V of x. Okay, so that's another way of potential energy, another way of putting potential energy. Remember, 1/2 mv squared is equal to ek. Well, what if I do this? What if I multiply and divide this equation by m? That doesn't really do anything to the equation. It's still the same equation. But here's what happens. So I multiply and divide by m. Everything else is okay, the same. So I'm left with 1/2 m multiplied by mv squared. And I can write that as p squared over 2m, because it's a known fact that m times v is equal to the momentum, and so momentum squared over 2m is just another way of writing kinetic energy. So that leaves me with the total energy equal to p squared over 2m plus v of x. I can solve for momentum simply by going E minus V of x. I multiply this with 2m, and I take the square root, and I'm left with P. It's not really important to write the vector sign here, but I always write it to remind you that P has a direction associated with it. So P is also equal to h over lambda. Because if you remember, de Broglie said that matter and waves are equivalent, so the energy mc squared of a particle is equal to the energy m over c over, h over c over lambda of a wave. You can go ahead and solve that to get lambda h over mc, or in our case it will be mv because it's a particle, so that leaves me with h over p. Okay? So P therefore is equal to h over lambda. This is the substitution I made over here. So lambda must therefore equal to h divided by E minus V of x multiplied by 2m to the exponent 1/2. Okay, so recall that I left the Schrodinger wave equation up until this point. Okay, so I have 1 over lambda squared in this equation. But this equation is only for lambda, so if I want to go 1 over lambda, then I do the flip, or I reciprocate it, and I'm left with this equation over h. So I'm going to go ahead and make that substitution, and I'm going to get d squared psi of x divided by dx squared plus 4 pi squared, and then divided by h squared, because this was lambda, because I'm dealing with lambda squared, this sign disappears, and this gets a squared on it. Okay, so I'm left with this 2m e minus v of x. Okay, and then I still have a psi of x term is equal to 0. So stick with me. I know this might seem a little weird or maybe even hard, but it's really not that bad. And another important thing to note is that I'm always going to be dealing with h divided by 2 pi, h divided by 2 pi. So another important thing we do in quantum mechanics is we introduce a new variable or a new constant, h bar, and that is simply equal to h divided by 2 pi. So h bar is equal to h divided by 2 pi. So what I'm going to do is this term over here, I'm going to go 4 pi squared divided by 2 pi squared, and then on the bottom of this, or simply, sorry, I'm going to divide this by 4 pi squared on the top, and simply on the bottom, h squared, I'm also going to divide it by 4 pi squared. So on the top, I'm left with 1. But on the bottom, h squared over 4 pi squared is just h bar squared, right? Because h squared over 4 pi squared is just equal to h bar squared. Okay, so h bar is h over 2 pi, and h bar squared is h squared over 4 pi squared. So that means I can rewrite this equation as d squared psi of x divided by dx squared plus 2m e minus v of x psi of x divided by h bar squared is equal to 0. Okay, so now what I'm going to do is I am going to simply I'm going to do something slightly different here, and what that slightly different thing I'm going to do is this. I'm going to divide, or so-called, I'm going to multiply this whole equation by h bar squared over 2m. So I'm going to go, so the first term I'm going to multiply by h bar squared over 2m. Then the second equation I'm going to multiply by h bar squared over 2m. Okay, so when I do that, this term and this term cancel out, and these terms cancel out. Okay, so the reason I did that was I wanted to get the energy term rid of all the masses, and I wanna leave that with the derivative of psi squared. I want to leave that, or the derivative of psi, that's the term I want to have the Planck's constant and mass associated with it. So plus e psi of x minus v of x psi of x is equal to 0. Okay, so now I'm going to rewrite this a little bit more to e psi of x is equal to negative h bar squared over 2m. So I move everything to the other side except for e psi of x. And there's a reason why we do this, which I'll explain in a second. Okay, so this turns out to be my Schrodinger wave equation. If it doesn't make sense, leave it in the comment section, and I'll do this again because I know there's somewhat of tricky math used. We used a few math tricks, so first try going over the video once or twice. But if you think I didn't make it clear enough, let me know and I'll redo it. Hopefully better. But anyways, let's move on from this. So it turns out that there's a little bit better way to write this equation. Okay. I'm going to go ahead and I'm going to pull the psi x outside, and I'm left with this. Okay. Now I'm going to call this part h bar, which is the Hamiltonian operator. So two things, Hamiltonian and operator, probably two terms that you've never heard before, but those of you who've taken a course on mechanics know that the Hamiltonian in classical mechanics is another way of saying the total energy of a system. So we know this is the potential energy of a system, and it turns out in a quantum mechanical system, this is the kinetic energy. We'll talk about that in detail next or later, but it's important to note that you should be aware of what this is. So the Hamiltonian operator just represents the total energy of a system. So this equation can be written as E psi of x is equal to, or whoops, another way of writing it is H psi of x is equal to E psi of x. So H hat is the operator, and this is a more convenient way of writing the Schrodinger wave equation in operator form. Okay, so obviously I think one question that comes to mind is, what is an operator? What on earth is an operator? An operator is simply a mathematical operation that you do on another function. So basically, if I do this mathematical operation on psi of x, which is some function, so the mathematical operation is, add v of x, or sorry, the mathematical function is, a negative h bar squared over 2m, then you take the derivative, second derivative with respect to x, you add the potential energy, and you multiply by the function. When you do this operation, then you get the energy of the system E. Okay, so the operator is just a mathematical thing that you do on the function psi of x, or on any function f of x. You might add, that's a mathematical operation, you might subtract, you might multiply, you might divide, and so forth. So these are all mathematical operations. So simply put, this is a convenient way of representing the Schrodinger wave equation, that when the Hamiltonian operator acts on the wave function, you get the energy of the system and the wave function back out. Okay, so nothing happens to the wave function, but you get a constant, and that constant is what you want. In our case, it's the energy of the system. So I hope this helped. Next time we'll discuss the operators in detail, and again, if the video doesn't make sense, leave it in the comment section and I'll try to make it better. So last time we left off by deriving a pseudo derivation of the Schrodinger wave equation, and this is what we found. So you can review the last video to see how this was done. So if we simplify this equation a little bit more, you can see that I can take the psi of x outside, and then I have these two common factors left in the bracket. Then I see that this term is equal to E psi of x. Well, I can do this cool thing where I can take this whole quantity from here to here, and I can replace it with some other symbol, and I'm going to name that h hat. It has a name, which we'll see in a second. And then I'm left with psi of x, E of x, and psi of x right back out of the equation. Now this E, it corresponds to the total energy of the system. This h with the hat is actually called the Hamiltonian, or the total energy operator. Essentially, it just defines, or essentially it's just represented by the sum of the total energy of the system. We'll talk about that more in detail a little bit later. So as you can see, this equation and this equation only depends on time. So this is, sorry, only depends on distance or position x. So this is the time independent Schrodinger wave equation in its operator form in this case. However, there also exists a time dependent Schrodinger wave equation. So some systems evolve over time. Usually it's not so important in chemistry research, but it is also worth noting what this is because sometimes it is indeed very important. So the Schrodinger wave equation in its time dependent form looks something like this. And you can see that it involves a partial differential equation because it involves multivariables. We'll derive the time-dependent Schrodinger wave equation as we go along as well using the separation of variables method. So now to the main thing. What do we mean by an operator? So generally an operator basically is a mathematical operation that acts on a function, any function, f of x, let's call it that, to produce a new function, and let's call that g of x. And generally we can write it in this form. So you have the operator, it acts on the function f of x, and you're producing a new function g of x. So basically, like if you have a function x and you square it, you get x squared, which is a new function. So you operated on the original function x by squaring it, and the operation was squaring it, and the g of x, or the new function, turned out to be x squared. So we're going to do something like that again. So we have to perform the following operations while also identifying what f of x is. So for the first one, the operator is equal to this whole thing. And f of x is clearly e to the exponent IH x. Okay. So I can rewrite this equation as such. So I rewrite the operator as this. Okay. And then this operator will act on this function. So that means we'll first have to take the derivative of this function 2 times. We will have to multiply the function by 5 and then take its derivative 1 time. And then we'll have to take the derivative of the function 0 times. And then multiply whatever we get by the square root of 2. So the reason why I brought up this, kind of silly, but it's too important, it's to highlight something that we'll be using later on. So if I take the derivative of e to the exponent IH x, sorry, I wrote k, it's actually x. I was doing simple harmonics before, so I'm rewriting the wrong things. Anyways, the first derivative of e to the exponent IH x, or IH bar x, is simply IH bar multiplied by 1 multiplied by e to the exponent IHX. But you have to take the derivative of that one more time. So you're left with IH bar squared and then e to the exponent IH bar x plus 5 times 1 derivative of e to the exponent IHX, which is just 5 times IH bar e to the exponent IH bar x. Now here, you're asked to take the derivative 0 times. That's basically what it is. It's basically saying, take the derivative of this 0 times. So this is going to be a weird way of writing this right now, but it's to help out on an example where if this wasn't clarified, that might seem really hard. So if you take the zero derivative of something, basically you're taking the derivative of that thing 0 times. Basically, you just get the same thing out. So you're left with square root of 2 multiplied by e to the exponent I h bar x. Now you can simplify this a little bit further, and I won't do that, but you can do that. So the next thing is, well, here I have not just f of x, I have f of x and y. And it's equal to x cubed multiplied by y to the square, y to the exponent 1/2. You're asked to perform this operation on it. You're supposed to take the partial derivative with respect to y of this function. So if that's the case, that means you're holding x constant while taking the derivative with respect to y. This is how we usually do partial derivatives. So you're left with x cubed multiplied by 1/2 multiplied by y to the exponent -1/2, which is just the derivative of y to the exponent 1/2. So you can rewrite this as x cubed to the x cubed over 2y to the exponent 1/2. Now the last thing I want to highlight is here you have f of x is equal to a squared plus b cubed. Now the operation I'm asked to perform on this function is to square it. Well, if I square it, then I get this. I get a squared plus b squared plus 2ab. So a squared in this case would be a to the exponent 4 plus b squared would be b to the exponent 6 plus 2a squared b cubed. Okay, so this is the square operator. Now it turns out that operators, when they act on functions, they can produce meaningless results, as we just did. They don't have any physical meaning, what we just did above. It was just to highlight a mathematical concept. But sometimes when the properties of operators are known and understood, well, they can be used in certain ways on functions to yield meaningful information. So I'll tell you what that means in a second. In quantum mechanics, we will deal with only 2 classes of operators, linear and antilinear operators only. Out of the few classes of operators, we'll only have to deal with 2 classes. And in fact, right now, we will only deal with linear operators. Antilinear operators are used in more abstract calculations and theories. So what does it mean to be a linear operator or to be an antilinear operator? Well, it turns out an operator is defined to be a linear operator if it meets true criteria. The first criteria is that when the operator acts on a sum of 2 functions, it acts on both functions as such. So it'll act on f of x and it'll act on g of x. Well, the second rule is also that when this operator acts on some constant multiplied by a function, essentially you can write the equation as the operator just acting on the equation and the operator, or sorry, the constant being pulled out. So we'll discuss this in an example, but these are all important concepts. So this is what makes a linear operator. If you meet these 2 criteria, you're a linear operator. So with that in mind, is this a linear operator? Well, we know the classification of what a linear operator is. If a linear operator is one that if it acts on f of x plus another function, then it should produce this result. Okay, so if you put a constant c1 and c2 here, with this second rule in mind, I can rewrite this equation as this. So if you satisfy this condition, you are a linear operator. It just puts these two together and it rewrites it as one condition. Okay, so let's see if this operator satisfies this condition. So I'm going to replace the operator by the nth derivative operator, which is basically just take the operator an n number of times. So if it acts on C1 F1x plus C2 F2x, well, we see that we indeed get this result. So therefore, taking the nth derivative, the first or the second or the third or the 0th derivative of something, it does make it a linear operator, okay? So this is one example. The other is the square operator a linear operator? So we do it on the same criteria. In this case, I'm going to rewrite this a little bit shorthanded so that I can save time. So I'll get C1 squared F squared plus C2 squared G squared plus 2 C1 C2 F times G, which is indeed not equal to C1 F squared plus C2 G squared. Okay? So therefore, the square operator is not a linear operator. So the only other category of operators that is relevant in quantum mechanics is the anti-linear operators. I'm just going to briefly mention this because we don't even talk about this at all. It's just it's used more in abstract theories that deal with symmetry, for instance. One major unanswered question in physics is there ultimate symmetry? There is p parity or parity based on position. Parity just means symmetry. So there is p parity. If you take a particle, you can orient it into space, and the laws of physics are well maintained for that particle. However, the same is not always held for time because of entropy. Now, the entropy of the universe is always increasing. So if you go forward in time, you'll see that the entropy is increasing. Certain processes will happen in a certain way which favors positive increases in entropy. If you rewind that, or you take negative t, if you take this transformation in the laws of physics, then you'll see that not every process happens the same way back and forth. So there's really, the scientists aren't really sure if there is T parity, if it's maintained or not. In fact, it's a really complex topic, so I won't talk about it too much. So anyways, the time reversal operators used in these theories regarding T parity, for instance, are antilinear operators. And well, what makes an operator antilinear? It's if an operator acts on a constant times a function plus another constant times another function, then essentially you get this result, okay, where this is the complex conjugate of the constant, and this is also the complex conjugate of the constant. So if this equation is maintained, then the operator is said to be antilinear. Hello and welcome again. So in this video, I want to give you some more practice problems so that you get familiar with the concepts that we've been doing. And then I want to give a brief overview on the probabilistic nature of the wave function. So by now you should know that in quantum mechanics, we're going to be dealing exclusively with probabilities, right? From the double slit experiment, we saw that in quantum mechanics, we can't really know many things with 100% certainty. There are some things we can know with 100% certainty, but most of the things we can't know. So anyways, here's my practice problem. And the practice problem is show that e to the exponent ikx is an eigenfunction of the momentum operator. So remember, it's the momentum operator in the x direction because we're only talking about a one-directional system. So the question is, show that this is an eigenfunction of p of x. So first of all, I'm gonna quickly derive this operator so that it gives us some practice. So this operator comes from the kinetic energy operator, which is simply negative h bar squared 2m d squared over dx squared. And then I said that classically kinetic energy can be written as p squared over 2m. Using this substitution, I can say that p squared over 2m is equal to negative h bar squared over 2m d squared over dx squared. The 2m's cancel. So then I said that negative 1 can be written as I squared, and that's because I is equal to square root of negative 1. So if you square both of these, then you get this, right? So what I'm going to do is I'm going to replace this negative by I squared. Then of course I have h bar squared, then I have d squared over dx squared. So what this implies is that the momentum operator is simply I h bar d over dx. Okay. So now that we have the momentum operator, we are asked, show that this is an eigenfunction of p of x. Okay, so we know that any eigen problem can be formulated in this form. So we're going to use this prescription and we're going to solve this problem, and it's quite easy. So we have IH bar, which is IH bar d over dx. Okay, that's the operator, and the function is e to the exponent ikx, if I'm not mistaken. Yeah, ikx. And now we simply just do the math. So the IH part is a constant and really nothing happens to it. So you take the derivative of EI to the KX. And remember, how do you take derivative of functions that are exponentials involving E? Well, the E part remains the same, and then you take the exponent's derivative, and that's the whole rule. So we have IH cross. The derivative of ikx is simply ik, because ik are both constants, right? I is always equal to square root of negative 1, so it's a constant. K is some constant as well. It's actually the spring constant, but whatever, you don't need to know that for now. So this derivative is going to be ik, okay? And then of course we're going to have this e to the exponent ikx. So we can simplify this a little bit to get I squared h bar k wow, I'm so sorry, but what I did is um, I forgot a negative sign here. Okay, so there's a negative sign there, negative IH cross d over dx. So don't forget that negative sign. There's a negative here, there's a negative here, there's a negative here. So I squared is itself is equal to negative 1. So negative 1 times negative is just equal to positive h bar k e to the exponent ikx. So the eigenvalue is this, and this is of course the eigenfunction of the momentum operator. Now I really want to just finish off things by discussing two things. And the first thing is that the order of operators matter. So this is the first thing I want to talk about. So if you have two different operators, let's say we have A and B, then what I mean by that the order of operators matter is that if A and B are acting on some function f of x, then it is not always going to be the case that this relationship is true. There will be some special cases in which this will be true, but in the majority of the cases, you can't switch these operators around and expect the answer to be the same. Okay? So that is one really important thing, that the order of operators um, matters, right? So we can easily prove this by let's say making an example. Okay, so assume that a bar is equal to x squared. So this is also an operator. You might get a little bit confused. Let's say it's 3x squared. Okay, you might get a little bit confused, but all this operator is saying is multiply this by your function f of x. So this is also an operation, right? Mathematical operation. And let's say b is equal to d over dx, d squared over dx squared, right? Let's say it's this. So I want to see, is this relationship true? So first let's go 3x squared, so which is a hat, and then d squared over dx squared. And let's say this is acting on some function f of x. And I want to see, is it equal if I did d squared over dx squared and then I did 3x squared f of x. So are these two equal? No, they're not, right? Here 3x squared is acting as a constant and this derivative is only acting on f of x. But here this derivative is acting on 3x squared and f of x. So this is not going to be equal. So it's very important knowing that don't make this mistake, okay? You have to be very careful about the order of the operators. So that's something you should be mindful about. Um, it is helpful. So what I want to do is I want to clarify the derivation of the momentum operator, because I think some people might be confused about the sign that's involved with the momentum operator. So what I'm going to do is um, I'm just gonna derive it again, so you know that the kinetic energy operator is negative h bar squared over 2m d squared over dx squared. Then the momentum operator squared is simply negative h bar squared d squared over dx squared. Right? The two m's cancel. You should follow this along from the previous steps. So then I can rewrite this as negative IH bar d over dx times negative IH bar d over dx, right? So the negative and the negative become positive, and then I squared is just equal to -1. So then this relationship is equal to this. So just make sure that you know that the momentum operator is in fact negative IH d over dx. So I'm not sure if I made a mistake when I was deriving this originally. So just make sure that you keep track that the momentum operator is this. So now the last thing I want to talk about is the probabilistic right now it is very late where I'm at, so excuse my spelling. So probabilistic interpretation of the wave function. So I'm just going to explain this in a little bit of detail right now, just so that you guys have some familiarity with the concepts. We'll build on these concepts a little bit deeper as we go along. Right now I'm just throwing a lot of information at you so that you have an idea of what to expect. So if you see many things right now, then the next time you see them, since you'll be familiar with them, it won't seem so hard. So this is why I'm going to talk a little bit about the probabilistic interpretation before I've actually, before I've actually started talking about quantum mechanics in depth. So what this means on the surface is that psi of x alone, it has no physical significance. It has no physical meaning. So in fact, if I was just given psi of x as a function, it's useless to me. It doesn't have any physical meaning. It doesn't translate to the physical world. So what is the use of psi of x? Should I just throw quantum mechanics out of the window and be like, okay, goodbye. This is all you need to know about the field. Psi of x has no physical meaning. No, it would be very silly to do that. And the reason being is that psi of x doesn't have a meaning, but the square of psi definitely does. So psi of x gives us square of psi, right? Without psi of x, we couldn't calculate its square. So psi of x is extremely important, and it has a million other importances as well. So we'll talk about that later. But right now, what I want to tell you is for physical significance, psi of x doesn't really have any physical significance. The only thing that has physical significance is psi x squared. And what does psi x squared represent? It represents the probability density of finding an electron. Okay, so it just gives you density of finding an electron somewhere in space. So what I mean by that is, assume that psi of x, so let's say you have x and you plot it against psi of x. Okay, so if your function psi of x looks something like this, here, I'm just gonna extend this like this. So let's say psi of x looks like this. So then the graph of psi squared of x would look something like this. So this would get squared and it would have a bigger height. So here the answer would be 0 because at this point it's still 0. But now the square of any negative number is positive. So then this would look something like this. Okay, then I'd come back to the nodal point and then it would look something like this. So this over here is the probability density of finding an electron. So basically you're more likely to find an electron here, here, and here, and you're less likely to find an electron in this region, and this region, and this region, right? So that's what I mean by probability density. So one last thing is that, remember, density is equal to mass per unit volume. So if you want to find quote unquote mass, you have to go density times volume and it gives you mass. So some specific value. So same, if I don't want to find the density, but I want to find the probability of finding an electron or any particle. So if I want to find the probability of finding a particle, then what I have to do is I have to take my probability density and then I have to multiply it by some volume element. So here the volume element is simply just dx, right? If this was 3D, then it would be dx, dy, dz. But since it's only dx, this is going to be the probability p of x. in the region x dx, in the region of dx is this. So you can integrate this from any value a to b, and it'll give you the probability of finding an electron in that region of space. So I just wanna help us clear out terminology. So now for 2D systems, psi depends on x and y. So then the probability of finding an electron when in 2D space would be given by two integrals. So you would have psi x and y squared, and now your volume element is dx dy, right? So there's two integrals because there's two differentials. So each differential, so basically, really what this is that, one of the integrals you're going to be solving just with x, dx, and the other integral you're just going to be solving with dy. So it's nothing really too hard. It looks hard, but it really isn't. So now let's say, what if you have 3D space, and then psi is a function of x, y, and z, right? In this case, the probability of finding an electron in this 3D space is given by a triple integral from a to b, and you could change these bounds to something else. I'm keeping it very consistent right now, and this is how it will look like. And here the volume element is dx, dy, and dz. So you can see that it can get very tiring to write dx, dy, dz. So many times what we'll do is we'll call this volume element d tau. Okay, d tau. So d tau is equal to dx, dy, dz. So what we can do is we can rewrite this integral as this. Okay. So with this, I just wanted to show you how we'll be proceeding to, with this, I want to show you how we'll be finding probabilities, how we'll be writing out our equations, the logic we'll be using. So go over this, make sure you understand these basic principles because we're going to start building on these pretty soon.